All right, well, welcome everyone. My name's Ellen Rathke. I'm a professor here in the Department of Civil Engineering. My research interests are in geotechnical earthquake engineering. And as Robin said, I'm the principal investigator for Design Safe, the cyber infrastructure, and we look forward to seeing all of your published projects from this summer's work. Just to give you a little more background, I've been involved with natural hazards research for about 25 years. And starting in about 2000, we initiated a network like this for earthquake engineering called NEES, N-E-E-S. And I was involved since then. And then it transitioned to being wind and earthquake hazards. And so today we have NHERI. But what's really been interesting over that time is there are professors in natural hazards engineering today that went through the REU program for NEES 15, 20 years ago. So you guys really are the future of our profession. And so we're really excited that you took the opportunity to do some research in the summer at one of the facilities and are here today to present what you did. So just think there's a lot of places you could go after this, and we're really excited that you're here. So with that, I'll turn it back over to Robin. I didn't give you enough time to.
It's okay, you're good.
Well, I'll do this. Do you guys have any questions for me? Yeah, go ahead.
How long have you been working with tech?
So when we submitted the proposal for NHERI Design Safe, which was 2015, that's the first time that I started working with them. And it's really been a great experience. What's really unique about TAC, in my opinion, I've worked with other computing centers around the country, is that their dedication to serve the researcher and their research interests. And so despite the fact that I hadn't used their facilities, the director of TAC, Dan Stanzione, was like, yeah, let's do this. He was a co-PI, brought in, we leveraged all the great stuff that's here, not just the compute, but the people. And I really think that's what's made it successful over the last few years that we've had Design Safe running. And we're really at a unique time now. A lot of people want to use machine learning. We've got the data that people are collecting in their experimental work that now are being saved and archived on places like Design Safe, so that researchers can come in and pull data from multiple places and then do all this sophisticated data analytics or computational simulation. So that was a really long answer to your question, which was 2015. But I'm a professor, that's how we go. Any other questions? Yeah.
Did you go undergrad, PhD right into academia, or what?
I did. So it's not always the route, right? It's always nice to maybe go out and work for a little bit. For me, it just worked out well. I got an NSF graduate research fellowship, so I went straight into grad school and then stayed on a PhD. And then when I finished my PhD, I got a job at Texas. So it's like, why would I say no to Texas to go out and work? So for me, that just worked really well, but I certainly think, so first of all, I think you can be successful as an academic without having gone out into working as an engineer. Having said that, there is a benefit for seeing real world problems. So even if you do go straight through, having some connection to engineering practice, through consulting, through what you see at different conferences, is important, so you kind of understand the problems that engineers have in practice. Anything else? Yeah.
Why did you choose geotechnical?
Oh, that's a great question. And how much time do I have, Robin?
Yes. Not forever.
Okay, I know. All right. It's a funny story because there are 2 times in my life where I just totally made a left turn, right turn. I wanted to be a journalist all through high school. I want to be Barbara Walters, if you even know who that is. And then at the last minute, I was like, wait, I like math and science and I don't like my English class. Oh, well, okay, math teacher, what can I do? Engineering? Okay, I went engineering. So that was good. But when I was a senior in college, applying to graduate school, I'd always wanted to do structures. I grew up in New York, buildings, bridges, everywhere. That's all you see. So I actually got further. I actually applied to graduate school for structural engineering. But don't take this the wrong way if you like steel. I took steel design and foundation design in the same semester. And the steel design was like, oh, And geotech was like, yay. So, I mean, I like, and it just shows that different strokes for different folks, right? There are some great researchers and friends that I have that are structural engineers. But for me, what I liked about geotech was, and some people hate this, the uncertainty, understanding how do we do the site characterization, how does that go deal with those uncertainties. Not that they don't exist in structural engineering, but I think what you learn about it as an undergrad, it's a much more defined as a structural engineer. So it was really the uncertainties and things like that that got me interested in geotech. So I called up all the grad schools, and fortunately they moved my application over to geotech, and it was okay. So, all right, I think Robin has stuff for you to do. I am going to hang out in the morning to hear your presentations. Unfortunately, I have some meetings in the afternoon and tomorrow, but I'm looking forward to see what you guys have. And if you have any questions at any of the breaks, just come and chat with me.
Thank you so much
You
for
bet.
sharing that with us.
Yeah.
Is supposed to be a template.
Hi, my name is Stephanie, and over the summer I worked at the Wall of Wind at Florida International University. And today I will be talking about my project, which is the investigation of peak wind loads on roof-mounted PV systems. So as a little bit of an introduction, the testing of photovoltaic or PV systems in wind tunnels are on the rise, and this is due to the fact that wind energy is becoming a more reliable energy source. But the testing of PV systems using scaled models in wind tunnels can lead to an underestimation of the actual peak wind effects in the field. And so the purpose of this study was to improve upon the current methodologies in place used to study roof-mounted PV systems. As a little bit of a background, the scales used to test PV systems in wind tunnels do not accurately simulate the turbulence spectrum. So figure 2 and the black curve is the turbulence spectrum, which is the curve representing the frequencies of large to small eddy sizes. So we see with smaller scales, such as 1 to 400 with the green line, that's accurately simulated within a wind tunnel. But with larger scales, such as the blue, which is 1 to 100, and the red, which is 1 to 50, the lower end of that spectrum is not really well simulated. And so the PTS method was developed by researchers at the Wall of Wind to mathematically account for and correct this mistake. However, this didn't account for wind-induced vibrations, also known as resonance. And this is just because most buildings do not experience resonance because they are more rigid, but PV systems do. And so the end goal is to make wind tunnel testing for PV systems more accurate, and to ultimately answer the research question of what is the best method to estimate peak wind loads on roof-mounted PV system. So this experiment involves large-scale tests of the Hogue Technology Center, or HTC, at Central Washington University, and this was performed at the Wall of Wind at Florida International University. So the Wall of Wind is a testing facility comprised of a 12-fan system capable of generating winds up to 70 meters per second. In figure 6, it shows a schematic of the Wall of Wind facility. It has spires and roughness elements to create turbulence, as well as a turntable. So on that turntable, we placed a 1 to 60 model of the HTC building, which was constructed out of plywood. And on top of that, we put a 3D printed model of a PV system. And we also put surrounding buildings featured on the campus, which is made out of foam. They were all attached to the turntable using magnets. So the way that this experiment was ran, starting at 180 degrees, the wind tunnel was turned on. It ran for an average wind speed of 9.5 meters per second. And then pressure data was recorded for 1 minute. And then it was rotated 5 degrees to 185. And the experiment was ran again up until 360 degrees. As for the pressure data, we installed 40 pressure taps in total, 20 on the top and then 20 on the bottom. And this is how they were numbered, and we only installed it on the top left array just to make things easier. So for data analysis, everything was done through MATLAB, and the variable that we focused on the most was the pressure coefficient, which is an instantaneous dimensionless number representing the relative pressure, and it's represented by the equation, where the top is the net pressure, which is the difference between the top and the bottom panel, and then the denominator is a version of Bernoulli's equation. And so this produces a pressure coefficient time history. This is one at 350 degrees, for the first tap. And as you can see, there's a lot of natural variability. So what we do with this plot for every tap and then for every direction, we take this and we take the average to get one singular point where we get the mean net pressure coefficient. A couple things to note, each color represents a different tap. The circles represent the top or the bottom 5 taps, and then the diamonds represent the top 5 taps. So the first thing that we see off the bat is that at 215 degrees, then 315 degrees, there are critical wind directions, and then specifically taps 1 and taps 10 experience the highest mean net pressure coefficient. The next statistic that we looked at was the peak. And so again, looking at this pressure coefficient time history, when we calculate peak, we're looking for the maximum peak and the minimum peak. But with this time history, there's a lot of natural variability. So it's not as easy as just looking and choosing the highest value and the lowest value, because that could be an anomaly. So instead, what we do is a best linear unbiased estimate, or BLUE method, which uses extreme value analysis based on the Fisher type 1 distribution. So for clarification of what I'm talking about, a maximum peak is positive, and that's a pushing force, and a minimum peak is negative, and that is a suction force. So figure 10 on the right is the maximum net pressure coefficient, on the left is the minimum net pressure coefficient. So again, each tap varies a lot when it comes to these peak pressures, but we know that at 315 degrees, specifically taps 1 and taps 10 again, that direction experiences the brunt of that peak of the net pressure coefficient. And then for the maximum net pressure coefficient at 215 degrees, taps 1 and 10 again experience the greatest wind forces. And so the next thing we did was area averaging, and we did this because we were looking at 10 different taps, and that can kind of be confusing. So if you want to look at the overarching idea of what's happening in terms of direction, we do something called area averaging, which will give us a force coefficient, which essentially, using the above equation, takes the pressure coefficient and it utilizes the tributary area of each pressure tap. So the yellow dots are the pressure taps. So we create divisions vertically and then horizontally. And then when we see the area that they encompass, they're slightly different depending on where they are. So using this equation, we get this resulting graph, which is a generalized idea of what's happening for the mean, the maximum, and the minimum depending on the direction. And so again, we see that at 215 degrees and at 315 degrees, those are the most critical wind directions. So now for a discussion, what does this all mean? Again, we know the critical directions are at 215 and 315 degrees. For the maximum peak, this is at 215, and for the minimum peak, this is at 315. So what does this all mean? Well, these angles are where conical vortices are likely to form. Basically, conical vortices occur when wind hits a plane at an oblique angle, and it creates a separating wind, and this creates spiraling vortexes that start where that contact hits, and it kind of trails off in both directions. And so that does two things. It explains why at the oblique angles of 215 and 315 degrees, why the wind loadings are the most extreme. And also it explains why pressure taps 1 and 10 specifically experience the brunt of those wind forces. So in conclusion, the critical wind loadings occurred at 215 and 315 degrees. And this is due to coronal vortices, which play a role in the generation of high peak wind loads. And then peak wind loads are dependent on the location of the PV system. The closer you are to where the conical vortices form, the more likely you are to feel the wind loadings. So ongoing research, there's still remaining questions. We want to compare our findings to field data collected at the H2C building. The H2C building installs their own, they have been measuring their own wind field data for about 2 years. And so we want to compare our data to theirs to see if it's more accurate. And then also we want to incorporate residents. We want to see if there's still any remaining gaps in that method. And the next steps in research, we want to look at the entire PV array instead of just the top left. And then we also want to see how these findings compare with ASCE 722. Currently, the building codes for residents or wind-induced vibrations are based on more rigid structures. So it's possible that we can be underestimating the wind loadings for PV systems. My experience at FIU was really fun. The top left images are my first day. It was kind of a media day. They had the mayor and they had important people at NSF. I don't remember all of them, but we got to see a simulation of the wind tunnel and how strong it was, which was really cool. And the rest of the pictures is just of nature. When I was in Miami, I go to school in New York. It's a concrete jungle. So anytime I was in nature, I was taking pictures of it. And I also took pictures of the lizards because there were so many. So learning outcomes, my top 3 takeaways was just learning about current ASCE standards and how they can kind of be either overestimating or underestimating PV systems. I learned a lot about wind engineering in general. I didn't know this field really existed, and I feel like I'm coming back knowing so much more. And also I learned a lot in MATLAB. I took MATLAB freshman year, but I feel like with my experience at this program, it's even better. And so in terms of mitigating natural disasters, the ability to accurately simulate wind loadings on roof mounted PV arrays will lead to more resilient PV systems in the future. And in terms of my future plans, I plan on going to graduate school. I'm more interested in the intersection between climate science and civil engineering. And for my acknowledgements, I want to thank my faculty mentor, Dr. Arindam Chowdhury, and my graduate mentor, Johnny Estefan. He was an amazing mentor and teacher. I learned so much from him. So I want to thank him for that. I want to thank the Waldman staff, Walter, Miles, Jimmy, Dr. Jing Chan, Manuel, and Dr. Diaz. They were extremely welcoming and they helped us be more involved with all the testing that was done. We got to work on other projects while we were there. I want to thank Carolyn Robinson. She helped me specifically with housing towards the end of the semester. And she was one of the first people that I met when I came to Florida, and she was extremely welcoming. I also want to thank Robin Nelson for everything, for hosting all the meetings, all the feedback, and just being there all the time for us. And also I want to thank the Natural Hazards Engineering Research Infrastructure Network and for the NSF award and for allowing me to be at the Wall of Wind Experimental Facility.
Are there any questions for Destiny? Destiny, you might want to ask people online as well.
Oh, any questions?
I have a question. So how much involved were you in the experimental work versus the data analysis?
I was not there for the experimental work. When we got there, it had just ended.
Okay.
With that being said, the Waldman staff, we were involved with other projects that were also there. So I feel like I did get a lot of experimental experience, even though I wasn't specifically working on my project.
That's what's great being a big facility.
Yeah.
Like that, where there's always something to look at and work on, and to see. So
Yeah.
great.
My name is Alejandra Reyes, and today I will be presenting my project on damage observation and experimental investigation of results on coastal crossings. So to introduce my topic, I will be talking about damage observations from hurricanes only. So one of the hazards that come from hurricanes are wind and especially high wind speeds, and these affect the components and cladding and main wind force resisting systems. So essentially they just damage the components of the houses that maintain the houses and keep the houses together. Also the exterior parts of the houses, such as the roofs and the walls. The next thing that comes with hurricanes is storm surge. So storm surge is essentially when seawaters rise above the expected elevation. And this can not only cause a lot of flooding, but a lot of more damage to the houses, which can essentially wipe them out. So in this image, you can see that the houses are completely wiped out, and that's not only from flooding, but also from storm surge, because they're tied together. So my project was specifically on Hurricane Michael, which took place in 2019. And overall, there was $25 billion in damage costs, which led to 45,000 damaged structures and 16 direct deaths in total. So my project specifically investigates the damage on slab-on-grade houses, which are houses that have no elevation compared to elevated houses. So this chart, this bar chart represents damage dates ranging from 0 to 4, with 4 being the highest. And as you can see, elevated houses received a high percentage of damage at a level 4, which represents the issue that I'll be discussing in this presentation. And similar observations were made in Hurricanes Irma and Harvey. So as for the problem, recent hurricanes have heavily damaged elevated houses, and building codes have minimal information on the structural expectations for them. So the hypothesis is that slab-on-grade houses are more prone to experience damage from flooding and storm surge because they are at a lower elevation. However, elevated structures receive heavier wind loads because there is less corruption with higher elevations. So the purpose of this investigation is to investigate the impacts of wind from hurricanes on elevated coastal residential buildings and compare their performance to slab-on-grade ones. And this could accurately determine wind loads, which can lead to the construction of houses with better performance under natural hazards such as hurricanes. So for this experiment, the wall of wind at Florida International University was used, and it is capable of producing up to Category 5 hurricane winds on the Saffir-Simpson scale. And as for the experimental setup, this is the arrangement for it. So the wind turbines are here, and the wind blows in this direction to the turntable with the models placed at the center. And this turntable rotates from 0 degrees to 360 degrees. But for this specific experiment, it was only tested from 0 to 90 degrees because it was a house, a regular shaped building. So the rest of the angles were measured based on symmetry. So as for the instrumentation, there were 4 models that we chose for this. And it was a 0 centimeter slope model, which is a slab-on-grade prototype, and a 12 centimeter elevation, 43 centimeter elevation, and 73 centimeter elevation. And all these houses represented a low-rise gable roof building, and the roof pitch slope was 18 degrees. And to examine the effect of elevating the structure, they were placed on 4 stilts, one on each corner. And it was a length scale of 1 to 5. And each house, in order to measure the pressure, there were 375 pressure taps connected for each model, and scanning valve scanners were connected to them so that they could measure pressure time history. And co-repose was also a device used to measure wind velocity profile. So this image represents the pressure tap distribution for each model. So the black dots represent each pressure tap, and in total, like I said before, it was 375. So in order to carry out this experiment, peak pressure coefficients, which are dimensionless values representing the relative pressure within a flow field, were calculated to use using this equation. So CP peak is the peak pressure coefficients and equals the peak differential pressure over 1/2 times air density times a 3-second wind gust at the mean roof height. So moving on to the results, I will be discussing the floor first because that seems to have the most impact overall. So these are 3 contour plots, and the key on the left represents higher and lower pressure. So the higher the pressure, it was leaning towards a more red color, while the lower pressure, which means negative pressure or suction, was leaning towards more blue, of a darker blue color. So as you can see in the 12 centimeter model, there was at the center, there was less suction, but there was also not as much pressure either. It was leaning towards the middle of this key. But as the area moved towards the corners, towards the stilts, we noticed a lot more negative pressure, so suction. And there wasn't a plot for the 0 centimeter model because there was no data to be recorded since it was on the floor, but the rest of the 3 ones do have elevation, so there was data to be recorded. And the 43 centimeter and the 73 meter model have similar plots, but the 73 model had peak pressure coefficients values that vary from negative 1.95 to negative 3.4 with a maximum pressure of 0.7. So as you can see, the negative pressures kind of outweighed the positive pressures. So there was a lot more suction, of more of a cooling effect than more force being applied to the floor. Next, I will be talking about the walls. So these 4 images on the top right, on the top are the east end wall, so that's why they're labeled E. And the images on the bottom labeled S are for the south end walls. And the results remain pretty stable throughout each image. The walls, as you can see, one has a negative pressure while the other side has a positive pressure, and that's just because of the way the wind was affecting and hitting the wall. Obviously, it's hitting the wall from a certain angle, but from the other side, it's not receiving the direct contact, so that's why it's receiving more suction, because the wind airflow is pulling on it instead of applying pressure to it. So overall, the 0 centimeter slope model had a larger positive peak pressure coefficient, so there was a lot more pressure on that model. However, there was a slightly higher peak pressure coefficient within the 12 centimeter model. And overall, we noticed that lower regions had higher negative peak pressure coefficients, and that is because of the formation of vortices, which reinforce oblique wind directions, which cause, instead of applied pressure, a suction instead. So moving on to the roof. The roof itself remained pretty stable throughout all cases. So we saw there wasn't a significant change in peak pressure coefficients, but there was, however, high suction around the edges and the ridges. As you can see, this blue, the darker blue area has a lot more negative pressure, with high suctions being negative 3.8. So it almost got to the lowest scale of -4. So as for conclusions, specifically for the floor surface, it experienced the most change in peak pressure coefficients. There was more negative pressure, specifically near the edges of the columns, which is alarming because ASC standards and building codes do not mention how to avoid damage from suction within these areas, let alone the expectations for the design process for the floor surface at all of elevated houses. So both negative and positive pressures should be considered when designing floor surfaces, as well as in estimating the loading on the foundation. In general, suctions increased by 30% as elevations increased. And this is because of the introduction of vortices, like I had explained before, which causes less pressure and more suction near the corners. And this necessitates the urgency to conduct more parametric studies that further investigate the effect of suction and find ways to mitigate these effects. For the roof and walls, the aerodynamics seem to be similar for elevated and slab on grade houses. There wasn't necessarily a drastic change in pressures throughout these tests. Across all cases of the roof, there was more suction near its edges, like I had explained before, and more pressure towards the center. As for future work, it is recommended that to test with varying slope arrangements. So this specific test tested with 4 stilts, but there are houses that have up to 8 stilts, up to 10 stilts. So that could determine or affect the aerodynamics of the house. Also testing irregular shaped buildings, because we did test a rectangular shaped building, but irregular shaped buildings behave a lot more differently than regular shaped buildings. So that could be a factor that changes the results of this experiment. And testing partially blocked elevated houses, because elevated houses do have sometimes a storage unit underneath the elevation, which also affects the aerodynamics of the house. As for learning outcomes, specifically with natural hazards, I was able to investigate the effect of wind on large scale models. I'm actually from Miami, so I come from a lot of hurricanes. I've experienced a lot of them before. And I've always been kind of fascinated to see how buildings can be built so that they could avoid and withstand the effects of these natural hazards. So I feel like this internship was very informational for me. As for accomplishments, I successfully performed damage observations and learned fundamental concepts of MATLAB, because I had no background in MATLAB before this, but I did learn a lot about how to use it and the fundamentals of it once I began this internship, which is going to be very helpful for me in the long run. As for future plans, I did gain valuable research experience, which enhanced my motivation to attend graduate school after completing my undergraduate degree. I am a rising sophomore, so I do have a lot of time to make a decision. I was initially considering to work in the industry, but based on this internship, my route may have changed. I still have a lot more time to think about it, but as of now, I am considering graduate school and both working in the industry as well. So I would like to thank the National Science Foundation, a part of the NHERI program. I would like to thank Dr. Robin Nelson for her guidance throughout this program. A special thank you to my PhD mentor, Haitham A. Ibrahim, and faculty mentor, Dr. Amal Alawadi, for supporting my participation in the study. Also, my parents, thank you guys, all of you, for watching my presentation. And FIU, the faculty at FIU, this image was the first day. We had a press conference on our first day where leaders from FEMA and NSF were there. And I thought it was a very cool experience. And overall, my experience at FIU was amazing.
Happen to know what like your average reference length was on your test, like the xenon value?
I'm sorry,
You know what the xenon value was on the test?
I don't actually. More questions?
Did you say you're a rising sophomore?
Yes.
So I'd love to hear more how you felt like you were prepared for this. So you did some great work, you used MATLAB, you have that experience?
Yeah, so it was pretty overwhelming coming into it because my mentors and stuff told me I had to like download MATLAB. I had no experience with it. The most experience I have is Python. So it did help a lot, but that's about it. But it was a challenging experience, but at the end of the day, if I did this, I mean, as a sophomore, then I could do a lot more in the coming years and in the future. So I think this is just getting my foot in the door.
Yeah. Well, and it showed, I mean, we promote Python here, but it shows you that with those coding skills, whether it's MATLAB or, you know, if someone, you know, other coding languages, you can pick it up pretty quickly. So that's pretty neat to see.
Any other questions?
So did you find that there was a statistically, like that there was a correlation between pressure and height? It ended up not being the case, right?
Yeah, so for the roof and the walls, there wasn't necessarily a difference in the aerodynamics of the house. They behaved pretty similarly, but for the floor specifically, there was a big change in the pressure coefficients. So that is a determining factor on other houses that could be built, because we've noticed that for past damage observations, the houses have a lot of like pulled floors from the bottom. So that is the difference, the main difference from the elevating heights.
Are elevated houses still like commonly being built along the coast, or has it been like?
No, yeah, they're still being built because if you don't have an elevated house, the seawaters rise with hurricanes a lot. So it just completely wipes out and floods the houses. So we'd rather have them elevated, but the thing is that the wind is more strong at those heights. But right now, in ASCE protocols or standards, it is recommended to elevate the house, especially by FEMA as well. They recommend elevating the houses.
All right, so hello everyone. My name is Leonardo Plinsa, and I'm currently an undergraduate civil engineering student at Rensselaer Polytechnic Institute up in Troy, New York. And this summer I was fortunate enough to be a part of FIU's Wall of Wind and do some experience there under the mentorship of Mr. Manuel Matis and Dr. Yanis Zizes. And today I'm going to be presenting to you on the visualization of a separated flow on a canopy attached to a mid-rise building. I know it's a mouthful, but I promise you guys it's really not that difficult. So if we go to the next slide, I just want to go through a rundown of what we're going to be covering today. So we're going to start with the background. What do you really need to know to understand what my project is about, how we conducted it with materials and methodology, what we found from it, and what does that mean in the resulting discussion. Then we'll conclude and then talk about the future research. And then I will end with my experience at FIU, and then we'll go into acknowledgements and references. So background, what is this all about? So basically my whole project is about canopies, right? And canopies, we put them on buildings to provide protection against the elements, you know, rain, wind, snow, shade in the sun, you know? But during extreme wind events, they're really prone to failure. And this happens during like tornadoes, hurricanes, especially being in Florida, hurricanes are a big thing. But there's a lot of failure, and you can see that in Hurricane Ike. But when designing canopies, wind loads really need to be carefully considered, because those are what's really causing them to be failed. So a main component of their failure is flow separation, right? And flow separation is basically a consequence of a fluid's inability to make a change in motion. So if you can see in this diagram over here, if the wind is coming from this direction, it will hit the let's say a canopy, and it will stop. It'll come to a stagnation point. And as it will go either up or down, let's just say we're following this one that goes up, the wind that's coming from this way is also pushing it as well. So it kind of doesn't really go on the surface, the top surface of the canopy, it kind of like flows over it sort of. And it creates this thing called a separation bubble, right? And in the separation bubble, there's a lot of turbulent and circulatory flow. So it kind of moves in a circle and it kind of gets, it's just random, you know? And the highest pressures, or not pressures, it doesn't produce a pressure, it produces suction. So it's that pulling effect on the front of the canopy. And what we've really known is that the highest suction effects occur closest to where the separation occurs. So right at where the wind is coming from, this is the highest, and these red arrows kind of represent that magnitude of the suction. But and flow separation is considered in designing all kind of buildings, the roofs of buildings, and such. But recently, they haven't been on canopies until recently, and they were added into the building wind standard codes of ASC 7. So we'll get a quick history about the ASC 7. So before 2016, canopies didn't really have, they were kind of treated as roof overhangs, not actually like a canopy. And that really led to them being over-designed, waste of material, waste of money. But during some research and in the 2016 edition, a lot of design guidelines were introduced for canopies, but only attached to low-rise buildings. So anything under 4 stories, right? But after this most current edition in 2022, more research has been done to kind of improve that for anything higher than those 4 stories. But during the research, something very interesting was observed. So if we take a look at this codification study done at the Wall of Wind, they're really looking to address the lack of code for mid-rise buildings, especially. And they had 2 different canopy lengths and 2 different story buildings. And they're really interested in the design wind loads. What are we designing our wind loads for canopies to be, right? And look at this figure right here. We can see a little figure of the model that they were testing on at the Wall of Wind. And what they found were like the factors that the canopy pressures were most sensitive to. So the length of the canopy, the wind direction, the canopy height, etc. But for a specific scenario, so we have the wind coming from this leftmost side, the highest suction pressures occurred in the center of the canopy. Oh my gosh, Bernard, did you lie? Like, what are you talking about? No, what happened was, this is a phenomenon. This is not expected, right? So if you look at this contour plot, if the wind's coming this way, it's a top-down view of the canopy. You see like the highest, the lightest colors is where those high suction regions are in the middle of the canopy. And they kind of hypothesized that these separation, that the separation bubbles from not only the canopy, but also the building itself was kind of interacting in a way to make these suctions happen in the middle of the canopy. So my purpose of my study was to visualize this flow and provide a more understanding of what is occurring in that center area. And really to try and support what they thought, the hypothesis is it the separation bubbles interacting is that was causing this. And this could possibly lead to a clear understanding of what happens when separation bubbles interact with each other, and also on a whole lead to like safer designs of canopies and balconies. So let's go into the materials and methodology, how we decide to test. So the design and construction of the model, our model was based off of their model that we did, but it was just at a smaller scale. We're testing in a smaller wind scale, so a 1 to 100 scale. And the case we selected was just the 8-story building with a canopy that was half its frontal length. So it was just half of the length of the building. But it was first modeled in AutoCAD, and then it was cut using a CNC machine. And then the canopy was 3D printed. And the height of the canopy was about 10.7 centimeters from the ground on the model scale. And the parent building was constructed using plywood, so it was 7/16 of an inch thick. And the canopy was 3D printed using polylactic acid, which is a fancy way to say plastic. So wind tunnel configuration. So in order to get accurate results, you need to configure a wind tunnel to make sure that it represents what we feel out here, is the little scale building feeling what the big scale building feels, right? So the velocity of the flow is measured using this Cobra probe. So if the wind's coming from this way, they measure the velocity and we put them at different heights so we can get that different heights, the velocity of the whole wind tunnel. And at the roof height, which we call the reference velocity, which we refer to, was 9.33 meters per second. The pressures were obtained using this pitot tube, so the wind coming from this way, and it was connected to scanning valve software to take those data, and we can make graphs that you'll see later. And it was tested in open terrain. So, in long story short, we're testing at higher wind speeds than we're actually feeling here. And if you look at these graphs, these are the graphs of the wind tunnel that we took from that data to basically show that this is accurately representing what we feel outside. So this is the power spectrum density, and this basically talks about the frequency of the gust size. How much power do they have? How big are they? How frequent are they? And these red lines over here are the kind of the range you want to be in, and our blue line is the data. And again, wind is a really sporadic in nature, as you see from the other things. And you kind of need to average it. So the red line shows the average, and you can see that we're fairly close to what we're looking for. And then over here shows the velocity profile. So as you can see here, this is the height, and this is the velocity, right? And the velocity, as you get higher, it gets faster, and that's because there's less obstructions, there's less buildings, there's less trees, less houses, less people to kind of make the flow kind of slow down. And the turbulence profile is the complete opposite. So the higher you are up, there's less things kind of obstructing the flow, but as you get closer to the ground, it gets more turbulent. There's more buildings, again, more people to kind of make the flow more turbulent. So testing procedure. So basically, what is flow visualization? It's a video. We blow smoke and then we record it, right? And that shows us what the wind is actually doing. And we have 3 cameras placed in the wind tunnel, connected to DeweySoft software to sync all of these videos together. And we have 1, 2, 3. You can see the locations over here. But if you can see in this video over here, the building is actually, the canopy is over facing this way. So basically, this camera was useless. It didn't really record anything of use, but in the wind tunnel, we did 2 tests of 60 seconds. And the way we got the best flow visualization was having someone in the wind tunnel holding the smoke machine right there. And obviously this isn't ideal, but if I learned anything being at the wall of wind is that you have to work with what you got. You know, being engineers, we have to figure out ways to get things done, and we got it done. So what did we actually get? Let's talk about the results. So we're gonna look at that first front view of the canopy. And as you can see, this is the contour plot from earlier. And again, the area of interest are these lighter regions where the higher suction occurs. And you can see kind of that there's maybe like a tornado or something. I don't know, but it looks funky. It's like something's going on there, but this doesn't really tell us anything. And if you look at another view, again, the same contour plot, like over here, like the smoke is like kind of missing. It's not there, but again, it's just a picture. And because of like wind's nature, it's really turbulent. Pictures don't do it justice. You can't figure out what's going on with wind with just a picture. So we're gonna look at a video from the top view and see what happens. So as you can see, it's fluctuating. So as you can see, this is that flow separation I was talking about from the building, and it's kind of fluctuating around here. You can see it kind of. It's like, I mean, you guys see it. I feel like you guys see it because it goes out. But if we put the contour plot back on it, you can see that it kind of follows. I changed the colors, by the way. The red and the yellow are those high suction regions. It kind of stays within that kind of region. You see, yeah, you can see it stays within that region. But again, that doesn't really tell us anything. You know, it's a coincidence. Is it real? Like, what are we seeing here? So, and that third camera angle is useless again. So what do? We got a special angle. We had the person in the wind tunnel recording, and they got to actually get a good angle of what we're seeing. And here you can really see what's going on. And you see those kind of like tornadoes almost. You see the wind's going this way, and it kind of turns around and tries to go back on itself, even though the wind is coming from this direction. So something is going on there. And then when we compare that to the actual pressure data, you can see that it actually occurs right where those high suctions are. And you can see like the tornado, the suction separation comes from this way and wants to go this way, and the separation also comes from this way and wants to go this way and wants to like rotate this way, so that there's an interaction, and that's where that tornado comes from. So what does this mean though? Why is this useful? What can we do with this? Well, basically the flow visualization, it confirmed that the regions of high suction were real. It wasn't just a fluke. It wasn't just something special. And it appears that when the flow goes over the canopy, that those 2 separation bubbles from the canopy and from the building do interact in some way to form those vertices. But where do we go from here, right? And we go to PIV, particle image velocity tree data to be obtained, which basically tracks the particles of the canopy and determines their velocity vectors, where they're going, how fast they're going, and we can use that can aid us in designing against those kind of things. And we can also do CFD modeling or computational fluid dynamics modeling, which can visualize in the aid of flow, which basically is a computer basically showing us where the particles are going, and it's a nice, better visual of what is going on. So that is it. That's it from the research. But how's Florida? How was my experience? It was good. I had a really good time in Florida. I'm not experience like Miami and all of it's like hot, humid, sweaty, boring. But the palm trees, the lizards, the FIU campus is beautiful. I will say that. And the first day there was like a big wind. It was the first day of hurricane season. They had a huge thing going on. And I got to spend a lot of time with other RUs here. Went kayaking. I got to talk to some people in NSF. But I think the highlight of my trip for me is I got to feed turtles. So I don't need to see them. They're living life. But what did I really take away from being at FIU? And that's well, one, I want to give a huge shout out to the Wall of Wind staff because they really did help me with my technical skills. And I really got proficient in AutoCAD, 3D modeling, and 3D printing. But I also got some experience with Fusion 360, CNC machining, and even video editing. And I got to be exposed to the testing procedure in wind engineering, watching them do large-scale experiments, and then even conducting my own experiment. But I feel like the biggest takeaway I have from this whole experience was to be proactive in my learning. I want to be able to, everybody's busy, everybody has things to do, but you have to go out. If you have something to do, you have to go get it done. Go reach out to the people who can help you get those things done. And I was also exposed to some really great minds in wind engineering to help, foster my knowledge. And I'm really excited to just take my experience back to my home university and develop as an engineer. As for the acknowledgements and the references, I have a lot of people to acknowledge, and due to the interest of time, I will, I'll kind of skip over it, but just think, if you think you deserve a thank you, you've got one, okay? So anyways, here are my references, and thank you guys. So if any questions? You have a big one, yes.
So I heard that FIU's facility has PIV technology. Why did you choose, or why was it chosen to do this smoke analysis as opposed to PIV?
No.
Money?
I had to, PIV, it takes a lot of time, and we don't really have time. I was there for 2 months, and we just got the data, so it was just interest of time. It was easier. I'm an undergraduate. I don't have all the experience, all the knowledge, so it was just easier for everybody that way. Any other questions? Yeah.
You said someone went inside the wind facility to record.
Yes.
Are they allowed, are they gonna?
Yeah. No. So this one tunnel was a lot smaller. Actually, he built it. Like he went through the whole process of designing and building it, all the electronic stuff. So he knows it in and out, and it was fine. It's like if it was a windy day, like if your umbrella's not flying away, it really wasn't that bad. So any other questions? Another one?
So in the smaller wind tunnel, did you have the same extremely high wind speeds as in the wall of wind? No?
No, everything is scaled down, especially when you use smaller models. You have to scale it down to smaller winds, so you feel that it feels the same relative pressure or velocity that you would feel at the large scale. So yes.
That's using Reynolds scaling, right?
Yes, of course. So but that's all technical stuff. Nobody wants to hear about that.
It's not true.
Okay, well, maybe it's 2 of you. Any questions? Anybody else online?
Thank you so much.
All right, good morning, everyone. My name is Lindsay Trask. I will be a junior civil engineering student this fall at Rensselaer Polytechnic Institute, and this summer I spent at the University of Florida's Boundary Wind Tunnel researching the prediction of peak pressure coefficients using higher order statistics with machine learning. So what is a boundary wind tunnel used for? Well, the technology in them allows for the replication of field conditions to be able to test things like scaled models, as well as create databases. And the wind tunnel provides a method that allows testing to ensure that these structures can be designed to withstand these expected wind loads. So by controlling the terrain allows to create friction along the ground, mimicking things like trees or hills or houses, things like that. And the application of machine learning to this boundary layer wind tunnel testing allows the rate of data analysis to match that of the data collection. And using an artificial neural network, Incorrect, sorry, I got ahead of myself. The research discussed in this project is a continuation of the higher order turbulence project, which has been a focus of my faculty mentor, Dr. Kurt Gurley, and my PhD mentor, Mariela Ojeda-Tuz. The goal of this research has been to investigate turbulence statistics to quantify statistically equivalent terrain formations. So a little background on the state of research in this field. A lot of research has been focused on peak pressure coefficients, which are non-dimensional metrics that reflect the relative pressures on a surface. And it's given by this equation. Research is focused on things like pressure distribution, flow rate attachment length, and free stream turbulence. So the application of machine learning allows the rate data analysis to match that of data collection, and using these artificial neural networks, which consist of layers of hidden neurons that ingest the data and perform nonlinear operations on the data to produce the desired outputs, allows a lot of complex relationships to be investigated. And seen in figure 1 is like an illustration of these example neural networks, where both the number of hidden layers and the number of neurons within them can be changed depending on the desired outcome. And neural networks have been used to predict things like the relationship between wind speed and wind angle to corresponding pressures. And figure 2 displays a contour map of predicted pressure values for an example low-rise model, which is just a common way of showing these pressures on these structures. So the purpose of my research has been to apply machine learning to boundary layer wind tunnel testing to explore these complex relationships between terrain formations and corresponding pressure turbulence statistics and pressure loads. And these peak pressures are an important factor in determining things like building codes with like the ASCE 7, which describes design loads and combinations. And therefore the ability to predict these pressures based on simply approach terrain would increase the application and precision of these codes. And my specific research questions were, can machine learning be used to predict pressures on a building if just the terrain, approach terrain is known? And is there a learnable pattern between terrain and pressure that can help us design? So the facility I worked in was the University of Florida's boundary layer wind tunnel. Consists of 1,116 individually controllable terrain elements. They rise out of the ground in 1 millimeter increments up to a maximum height of 160 millimeters. And the computer controlled gantry, which you can see in figure 4, has various measurement instruments on it, like velocity and pressure probes that allow data collection through that entire test section at the end of the tunnel, which also includes a turntable that these models, like the ones used in this research, can be placed on and tested for any of those wind directions. So the models used in this research include 2 low-rise bluff body models, the first being 250 millimeters tall. These 2 figures just show the pressure tap layout. And the first one has 339 pressure taps on it, 99 on the top roof and 60 on each of the sides. And this model was tested prior to the summer and is the data that I worked with for my research. And the second model, which is 500 millimeters tall, has 499 pressure taps, 99 also on the top, but then 100 on each of the sides. And this model was tested using the same process, but only started getting tested like a week ago. So I didn't really access this data. The software that I used was MATLAB to just analyze the data and build the neural network. And then the method used was done in 3 major steps. First was focusing on data collection, then we moved on to the data processing, and then finally bridging that gap between inputs and outputs using the machine learning tool. So data collection was then further segmented into 2 phases. The first being focusing on velocity data. This didn't have any of those bluff body models. It was just the computer controlled gantry that collected wind time histories of the velocities. And this was first tested on 25 benchmark tests where all the terrain elements were set to 80 millimeters in height each. This was run 25 times just to create like a reference of data for the rest of the tests that were run, which include the 226 machine learning terrain configurations. Each of these has a different wave number and amplitude to define the sine wave of the terrain elements. And these were just decided on previous machine learning work. And then phase 2 focused on the pressure data, which included those 2 bluff body models, and each of these were run through 32 different terrain configurations of those 226, and then 7 different wind directions from 0 to 90 in 15-degree increments. So then moving on to the velocity data processing, we first wanted to create the mean and peak wind speed, turbulence intensity, skewness, and kurtosis profiles. And these just are statistics that represent wind fluctuation at higher orders. And then once that was done, we moved on to the pressure data processing, which focused on calculating those peak pressure coefficients and the corresponding statistical values. And then once that was done, we moved on to bridging the gap between the inputs and outputs with machine learning, which first focused on predicting those profiles. For this research, we just focused on peak wind speed profile, and then moved on to predicting the peak pressures on the actual buildings themselves. So for preliminary results, we first created these profiles for each of the 25 benchmark tests, where they were all averaged to create one smooth profile, and then just given equivalence bounds of plus or minus 3 times the standard deviation as a reference for the other machine learning profiles that we created. So once we did that, we wanted to see first, can we predict one of these profiles before we move on to pressures? So starting with a neural network that had 1 hidden layer and 10 neurons within it, we wanted to see which was a better way to measure this input, to input the data. So we could either input the data 1 height at a time of those 27 heights that each of the data were measured at, or input all the heights at once to create one smooth profile as the output. And after calculating things like the average absolute percent difference, standard deviation, coefficient of variation, which is just standard deviation divided by the mean, we found that inputting 1 height at a time resulted in fewer error and less failed tests, which were just based on an arbitrary value of error of 2%, just randomly chosen. And if you look at these 2 figures on the bottom, the one on the left represents machine learning experiment 211, which had a much higher value of error, closer to 2.2%. And you can see they don't really match up. The blue is the real data and the red circles are the predicted data, compared to that of experiment 103, for example, which had a much lower value of error, and those profiles match up pretty closely. So then once that was done, we moved on to, well, first we decided that inputting that 1 height at a time was the best bet. Then how did we want to configure the network? First, we used one of the metrics, which was the minimum pressure coefficient values, and a network that has 5 neurons, 10 neurons, and 15 neurons. And between the 10 and 15 neurons, they're both on the similar scale, and they have pretty similar results for error and coefficient of variation compared to that of the network with only 5 neurons, which had a much higher scale of error, as you can see the little red circles. And between the 10 and 15, we found that the errors were inconsiderable for what we were looking for. The one with only 10 neurons was the most efficient. So we continue forwards using that. We also did the same analysis for the mean pressure coefficient values, and the same results we're seeing from these. So we figured it was a good bet to continue forwards using the one with 10 neurons and inputting all the heights individually. So once that was done, we were able to predict this data. This plot shows an exploded view of the 250 millimeter tall pressure model at a 45-degree angle. This is the real data. And a yellow color represents that positive pressure pushing on the surface, and a blue color represents negative suction pressure. So this is the real data for the minimum peak pressure coefficient, and then this is the predicted data. As you can tell, they look very similar, very hard to distinguish between. And then if you actually look at the difference between these 2, you just subtract one from the other. They're pretty close on a very small scale, and pretty all close to 0, which goes to show that this was a pretty good prediction for this data, which is good because we're testing on what we trained it with. And then we did the same thing for the mean value of the pressure coefficient. This is the real data. This is the predicted data. And then again, this is the difference between them. These are even closer. They're all very close to that dark blue color, which represents no change. It's on a much smaller scale. So then once that was done for the benchmark test, we wanted to see, okay, can we predict things that don't have the same terrain element height all around? So this is the
data for experiment 3, which is just one that we chose. And for a 75-degree angle on the left, you can see the predicted data for the peak minimum values of the pressure coefficients compared to the one on the right, which is the difference between them. Again, you can see they're all pretty close to that 0 value. There's not really a big difference between them, other than these corners right here, which are just little errors. But other than that, it proves to be a pretty accurate representation of what we were looking at. So the research conducted this summer can prove to show that a basic relationship between approach terrain and the resulting pressures can be modeled, seeing that the neural network was able to accurately predict the data that it was trained with. A solid foundation has been created that can be built upon in the future. It's important to note that the analysis of these results are very qualitative in nature. They're not very rigid or anything like that, and any conclusions made about error were made arbitrarily just for like comparison's sake. And there are also many ways to configure and construct this network depending on the relationship you're investigating or what kind of results you want to see. So the one used here were just the basic MATLAB standard default settings, but you can open one door and then there's a million doors behind that. You want to change one little thing, it'll change what you get as your results. For example, in this case, we chose to use one height at a time to be input. That may make spatial interpolation between these 27 heights possible, but if you wanted some other result, you could have changed that depending on what you're looking for. So the next steps in this research involve obviously investigating this acceptable error to be able to actually produce those qualitative results and quantitative results to get more of a clear understanding of what's going on. And then also just collecting more pressure data to allow more complex training would help to create a more robust model, which the ultimate goal of this research would be to develop a model that allows the prediction of pressures for terrain configurations that weren't tested, as well as wind directions that weren't tested. And this would kind of give you free range of the conditions that you can test and just really increase the application of this research. And then also you could look into creating an ensemble network, which is a network that learns from that error that it calculates, and then it recalculates those predictions to create just a more accurate model for what you're looking for. So my experience at the University of Florida this summer, I had a great time. That top picture is me and the 2 other RUs and our faculty mentor, Dr. Kurt Gurley. And then these pictures on the bottom are just some fun things I did around Gainesville. Really great summer. I got to see horses, which was really fun. So my learning outcomes, my top 3 takeaways would be it's about the journey, not the destination. You should always enjoy the time while you're experiencing it. There's always more to learn no matter what, even if it's not something you thought you were going to learn about. And that progress is not linear. You can take 3 steps forward and you could be across the street. Like you can't really plan for that. And in order to mitigate natural hazards, this research can be used really to inform building codes once you're able to create that really advanced model. And being able to accurately predict these pressures in regions that experience really strong winds due to hurricanes or tornadoes or anything like that would really help prevent large scale destruction. If you know what these are, and you can prepare for them. And then my future plans include hopefully more research this fall at my home university, and also definitely continuing on to graduate school. So I would just like to thank my mentors, Dr. Kurt Gurley and Marielle, also Dan Lander at RPI for getting me here, encouraging me to apply, and also to Robin for setting this whole summer up, and to my friends and family for always being great supporters. And also thank you to NSF for funding this research. The end. Any questions? Anybody? Okay, yes.
Sorry guys, I really like wind tunnels. So I don't know if you had enough like data, like full trials, but did you see any patterns in where the biggest errors were?
It depended on like wind direction. I think some of them you could see a clear trend where the difference between the real and the predicted data, you'd have like, you're at a 45-degree angle, for example, you'd have like this darker or lighter, you just have like a clear difference between them. Whether or not that's a big difference or not, I'm not sure. We didn't really look into that. We also briefly looked into looking at the directions between the ones we actually tested, but we didn't have data to compare that to say, okay, this is a good representation of what this would be or not. That's why like collecting more data would be really helpful, because then you could not train it with that data and then test it on it and compare them together and see if it actually was a good prediction or not. Yes.
On the slide where you have like the two buildings laid out with all of the pressure taps,
Yes.
I noticed in the one that's taller, they're like much further apart, the pressure taps on the bottom compared to the top. Is there a reason why they did that? Let me see if I can do that. So.
Sorry. Okay, wait, there we go. Yes, okay, so the one on the left is the lower one, and on the right is the taller one. But since we would just assume that the data in the same sections on the ground, regardless of how tall the model is, would have the same result. You know what I mean? So we didn't want to spend time putting all those little pressure taps in if you're going to get essentially the same results. You're focused more on what's happening at those higher heights. So it was just to like save time and save data storage. It's a lot of data. Yeah. Anyone else? Awesome. Thank you.
Morning, my name is Darlene Torres. I'm from the University of Puerto Rico. This summer, I worked on my research titled Higher Order Turbulence and its effects on structural loads and response, specifically the study on experimental equivalence. And my mentors were Dr. Gurley and Mariel. It was my graduate mentor. We all, like Dr. Gurley, he is a professor in the University of Florida. That's where my research was this summer. And Mariel Ojeda, graduate student, PhD student, she's from Mexico. And I'm from Puerto Rico, and we just all happen to live in like really active hurricane zone. And like we're all working with hurricane data and experiment research. So that I found that to be pretty cool. So now I'll be talking about the motivation and background behind my research. The boundary layer wind tunnels. They research these, and what it does is like it has all boundary layer wind tunnels have a section that usually have like elements sticking off the ground, and what you do with that is you try to replicate a wind profile. And like depending on the environment that you want to like simulate, for example, like an urban environment, a wind profile in an urban environment is much different than a wind profile in a more rural environment. And then with that, you try to see the structural response in the model that you're studying. And the goal is to like update the building codes to create more resilient communities. So now I'll be talking a little bit of bluff body peak pressures, like the experiments behind it, how you obtain it. Bluff body is essentially like any body that has really sharp corners and cause like separation of flow, like Bernard mentioned earlier this morning. So first, boundary layer wind tunnels, they start making sure that the wind profile that they currently have for the research matches the target wind profile. So like and once they have the target wind profile for like the environment that specific environment they want to study, then they proceed to do the bluff body model experiments. In this image over here, you can see like the model, all the pressure taps, and like the little red dot represents just one pressure tap, and one pressure tap, from one pressure tap, you get the time history. So this is the time, the data, the actual data from the pressure tab, and that you with the data, you calculate the coefficient of pressure, and that coefficient of pressure for each pressure tab you process it over and over again until you create the exploded view. What you see here is like the error, the arrow that you see represents the wind direction, and the yellow region is like the positive pressure that causes like pushing motion, and the blue and violet region are like the suction portions. So like the problem is that so many different facilities are able to match the mean speed wind profile and the turbulence intensity wind profile. But they've noticed that for some reason, the peak pressures don't match, even if they have the same first and second order, well, the mean and turbulence intensity profile. So going over again, like this is what they call the first order, the mean speed wind profile. This is called the second order or turbulence intensity wind speed profile. And like many facilities are able to match and have to match the first and second order to produce like meaningful data. But because it is difficult to control like higher order statistics, the third and fourth order that you can see here, the skewness and kurtosis, then they're much unlikely able to match those and control them, just because it's just this high, what they call a higher order characterization is much trickier, it's very time consuming. So usually this is disregarded, and there's a hypothesis and there's studies that suggest that like the discrepancies caused in the pressure models occur because of these higher orders that they don't match between different facilities. So my mentor this summer, he was working on studying that the higher order influence on structural response. And before I came there, to UF, they worked on the data acquisition, data collection. So first they started with the wind profile experiments. They started with the benchmark experiments. They did 25 different benchmark experiments, and then they averaged out the data, and they got an average mean profile, average turbulence intensity, and average like third and fourth order. And then they did what they called sinusoidal experiments. So I don't know if you guys can see, but the terraformer actually has simulates like a shape of a sine wave. And so they also did like many different experiments just to study the different wind profiles, and they tried to study which ones matched to the benchmark experiment, which had like all the terraformer elements in the same height. And having that data, they created this graph to kind of like generate a kind of like a map to determine like which sinusoidal experiments were equivalent in the second order and which were not. So there's some blue dots. Those were actually the experiments that were run, and they used machine learning to predict over and over again different experiments where they would run within this parameter space. So you can see like the y-axis represents the amplitude of the sine wave of the experiment, and the x-axis is the wave number of the experiment as well. And you can see like the green region is actually the experiments, the sinusoidal experiments that fall within that region are equivalent in the turbulence intensity profile to the benchmark experiments. And so once they had that, they wanted to look at the bluff body experiments. So they first repeated the benchmark experiments, but this time with the bluff body experiments. And then they did the machine learning experiments. So for that, they handpicked a couple of the experiments that the machine learning had generated to create the green region. And they ran the actual experiment, the sinusoidal wave, they ran it with a bluff buddy. And so my work was to look at the last experiments that were done and compare like what the one pressure tab, what each pressure tab from each machine learning experiment, compare it with the average benchmark experiments and see if they are equivalent or not equivalent. Are they the same or are they not the same? And if they're not the same, what does this mean? Like, does that mean that, could that mean that there are differences in the higher orders statistics wind profiles? So the problem is that there's many ways that you can define equivalency. So take the average benchmark experiments, right? Take one single pressure tap from it. You can either like take the data itself as it is, or you can process the data and like compare each individual benchmark experiments with the average experiments to obtain the mean squared errors. And then like having all of that data, you can then do either the Gaussian distribution, which is on the left side, or or the chi-square distribution, which is on the right side. And then for each of those distributions, you have to determine like a threshold, a line in the sand, like, and this threshold essentially defines like which pressure tabs are equivalent and which aren't equivalent. And then let's suppose that right now what you're seeing is like threshold at 90%. Now, if you play with the threshold and let's say you change it to a bigger range, 98%, the results may vary, like may be different significantly. So it's really important to define and study how sensitive like the pressure tap equivalency is to the definition that you put, because with this you can determine like, okay, so are these differences in peak pressures for different facilities, are they caused by higher order wind profiles, or is it something else entirely? And so having defined the equivalency, then you can proceed for each machine learning experiment to then determine for each pressure tab which pressure tabs aren't equivalent and which are equivalent. And this is also like considering 7 different directions and different metrics. So this is like one of the results for just one machine learning experiment in the 0 degree for the 250 tall model. So what I did for each of these models, I calculated what percentage of the pressure of the whole pressure tabs, the 300, I think it was 399. Correct me if I'm wrong. Okay, I'm good. So I calculated the percentage of which pressure tabs like were non-equivalent. And like each single, this is just a sample of the data, like in the table, each single cell represents just one exploded view. And I wanted to see like if there were any specific behaviors in those percentages or irregular like behavior. And you can see that, for example, this is just taking like the average of the machine learning experiments, and you can see that the machine learning experiments like the between 10 and 15, like around the 13, it was a big issue. And also there's a big problem, high non-equivalency percentage. And also you can see that on between the experiments around 24th and 31st. And then so this this was for the Gaussian distribution, and I got a similar result for the chi-square distribution, where there's like a very high peak in the 13 machine learning experiments. And these graphs, both of them are in the case of like what's the maximum percentage, because when I started looking at the models, I noticed that just if I only use the average percentage plots, I would miss some really interesting models. So going back to the machine learning, number 13 is actually pretty interesting because it's bowl shape. It's actually pretty close to the homogeneous terrain. So I'm wondering like why are the percentages are so high? And you can see here, so these are all like the row above represents the Gaussian distribution at threshold 98%, and the row below represents the chi-square distribution at 98%. And you can see that there's no, at least for the machine learning number 13 at 45 degrees, for both the mean metric and the maximum peak metric, those are pretty the similar results, if not the same. And so what the yellow represents is that it is non-equivalent in the positive direction for the Gaussian distribution. And if it's like in the case of chi-square distribution, then it's not equivalent because it only has like one threshold value. Like, and so like in my results will be used in the future, and specific irregularities will be used to further study those higher order irregularities to see if there's any correlation between like the non-equivalency and the higher orders wind profiles. And also this summer I learned that it's really important to have a clear statistical definition when performing research and establishing like a standard definition, because it allows like consistency in data processing, your methodology analysis, and having that consistencies allows better data quality, which leads to meaningful results, which can lead to improved codes and resilient communities. So just quick, I really have fun this summer. I was immersed in the nature of UF. Over there on the right is like Lake Alice. I also got the chance to go Universal Studios. I faced my fears of super high roller coasters. And so like top 3 takeaways. Research is a process of continuous learning, and it thrives on collaboration and networking. It's so important for different researchers to like peer review their work and make sure to study any like curiosities, any discrepancies between the data. Then this type of research helps with the improvement of building codes, like I mentioned earlier, which brings more resilient communities. And then my future plans, well, I plan to go to graduate school, and I plan to continue doing natural hazard research. I really enjoy this part. I'm from Puerto Rico, so I experience a lot of that on a daily basis. So I'm excited about that. I like to thank Dr. Gurley, my mentor, Dr. Jennifer Bridge, PI of UF, the boundary layer wind tunnel. I like to thank Dr. Robin Nelson. Like I would like everybody to give a round of applause for her. Thank you to Mike Masseret, my graduate mentor, like Marielle. I'd also like to thank Yuti for giving me some helpful advice with MATLAB. And thank you all for like helping like throughout this process with the peer review and making this whole summer experience super fun. Thank you, lastly, my family and friends for their continued support throughout the summer. This work, I also like to thank, the NSF and NHERI for providing the funds as well as the University of Florida. So thank you. These are my references. Any questions?
Thank you so much.
All right, so my name is Warren Haller. I was also at the US faculty this summer. I was on a different project called Project Sentinel with Dr. Brian Phillips. Let's get into it. So the Florida Coastal Monitoring Program, or FCMP, is an inter-university program, and we collect wind records for hurricanes. It's been going on for about 23 years now, since 1999. And so you can see with this picture on the left here, this is actually T1, so Tower 1. It's one of our portable weather stations that we use to take wind measurements in the middle of hurricanes. We take them out to the coast and park them somewhere, set them up with their anemometers, and we get wind readings. So on the right here, we actually have a wind record from Hurricane Harvey. This is not from the same tower that's here, it's from T2, which is actually a 15-meter tower. It's a little bit taller than the tower that's pictured here, but we see some wind records. We see, these are the wind speeds we see. Actually, in Hurricane Harvey, we saw full eyewall passage, which is super cool. So we see the eye of the storm pass over our measurement systems, and we see much lower wind speeds in the eye. So some background for this. So Project Sentinel, actually, we were working to develop a new class of portable weather station. This one here is a steel lattice tower, right? So that's really susceptible to storm surge flooding. If it floods, it no longer works. And so because of that, we have to set it back from the coast. And so you can see in this bottom image here, we actually have a denied observational environment. The denied observational environment is the environment where we're expecting flooding. And so we can't set up our steel lattice towers out there. And so we're working to develop a new class of portable weather station that we can actually set up right there, ideally on the beach, driven 20 feet down with steel piles, and it will get flooded. It's expected to be flooded, and it will still be able to handle that and give us great wind records of coastal environment. So this is actually a schematic of the Sentinel itself. We are constructing two of them currently. They're identical. So it's a 10-meter tower made of carbon fiber. It's a hollow carbon fiber tube. And we have 20-foot piles that get driven down to the beach. Various measurement systems, for example, at the bottom of it, at the base, we actually have a hydrostatic pressure sensor that detects how deep the flooding that we're experiencing is. And that really helps us to identify how high up our instruments are at any given point in time. But steel lattice towers, they're always at 5, 10, 15 meters high, right? Because they're not getting flooded. It's always 5, 10, 15 meters off the ground. The Sentinel, we actually have flooding. And so sometimes we may only end up with, 5 or 7 meters of instrument height. Also at the top, we have a bunch of other sensors if we want all sorts of data from these hurricanes. We have meteorological sensors, the video camera. Actually, we're working on setting up a LiDAR system up there, which would be super cool to investigate the way that the beach erodes during a hurricane. Also, probably most importantly, is the anemometers themselves that tell us how fast the wind is going. And in the case of the Sentinel, actually a triaxial tilt meter, because when we set this thing up on the coast, it's a big carbon fiber mast. It's expected to flex under all this wind and water loading. And so if our anemometers are tilting, then we need to be able to know how much they're tilting in order to resolve the wind speed. And that's sort of the main focus of the project here. On the right, we see an image of actually the Sentinel being set up. This was last November, just sort of a test run to set it up because we're preparing to deploy it this hurricane season. So like I said, the most important instrumentation here is our actual anemometers. And so they're set up in this sort of funky configuration here, which we're going to talk more about. But we have 3 anemometers, and they're set up in non-orthogonal positions. So that no matter what direction the wind is blowing relative to these anemometers, we want to be able to resolve our wind speed. So here on the right, actually, this is an experimental setup for when we actually do tests. This is a test that I did in the wind tunnel, trying to investigate the way that we are calculating our wind speeds from our anemometer readings, because it's a very chaotic environment. We still want to be able to resolve wind speeds. So the two main most important things for resolving these wind speeds are orthogonalization and rectification. We'll talk about both of these a little bit more in a bit. Effectively, orthogonalization is where we take our 3 non-orthogonal anemometers and we try to convert them into a orthogonal system where we can say, yeah, this wind was blowing north, or this wind was blowing east, or this wind was blowing down, which is our coordinate system, which again, I will discuss later. Rectification is where we deal with the tilting of the anemometers. And so if our anemometers are tilting forward or backward, left or right, we still have to resolve those wind speeds. And rectification is the process by which we do that using our tilting measurements. So we'll start with orthogonalization. Now, so this image on the right here is actually the anemometers themselves, their response to skew wind angles. So when the wind is not blowing directly, let's say, along the axis of those vane anemometers, those propellers, it's going to underreport the wind speeds. So if it's blowing at a 45-degree angle, that anemometer isn't going to tell us like, yeah, it's blowing at the speed that it is. It's going to tell us a smaller number. And so we want to be able to predict what actually it was, even when the wind angle is not straight down on it. And so the way we do this is with a coordinate transformation matrix. We know our positions of our 3 anemometers. We know the angles that they're set up at. And so we can use those positions to transform our coordinates from this non-orthogonal system to an actual orthogonal system, northeast down, like I discussed before. Northeast down is used a lot in aerospace. Other people might use like east north up or other coordinate systems. We're using northeast down because it works for the sun. And so the process by which we do this is we apply the coordinate transformation matrix, then we calculate based on what that wind speed that we just calculated was, what the angle between that wind and the anemometer would be. We have to check that against what we actually have. And if it's not correct, then we adjust for that. And that's an iterative process, and we actually use 10 iterations to see that it approaches the solution within 10 iterations. Usually significantly less than that, but doing 10 doesn't cost too much computation power, so we can. And so we apply these corrections and keep repeating this until eventually we approach a specified wind speed and wind direction, and that is our resolved wind speed. But this has not taken into account yet the tilt meter, in case our anemometers are not actually oriented horizontally like they are with steel lattice towers. And so now we have to worry about rectification. And so our tilt meter reports how far the mass is deflected at any given point in time. We're actually collecting 10 hertz, so we have a lot of data about that. We're expecting the sentinel itself to only vibrate at around maybe 2 to 4 hertz, 3.9 maybe, something like that. And so if we're recording at 10 hertz, that is plenty of data to be able to always tell what angle at which we have deflection. And so in order to convert from our orthogonalized coordinates into real life northeast down, actually we can tell you this wind was blowing north and not just forward from the sentinel, right? We have to know where the sentinel is so we can rectify that to the actual world. And what we do here is we use a rotation matrix. And so rotation matrices, I could talk a lot about math today, but I'm not going to. We are actually able to rotate our coordinates that we just calculated using our orthogonalization method into a globally rectified system. We have measurements of pitch and roll from the tilt meter, and then we also have a yaw measurement that actually is set when we set up the sentinel, because it's a big tall tower. It's really torsionally stiff, so it's not expected to twist back and forth. It's only expected to flex with tilt and roll. And so we can just set our yaw angle as just the heading of the sentinel when we set it up. And so we can use a rotation matrix here to rectify our measurement to a resolved wind speed and wind direction that is real world wind speed, wind direction. And so you can see in this bottom image as well, this is actually the tests that we use to try to validate this and investigate this and see how well we're actually able to predict these wind speeds in a really chaotic environment. So now we're going to look at the results of this test. So here on the top, we have the pitch test tilt meter history. And then on the bottom, we have the pitch test wind speed and wind direction history. And so we're going to talk about the roll test in a minute. The difference between the pitch and the roll test is one of them we're manipulating the pitch of the sentinel, and one of them we're manipulating the roll of the sentinel. And so there's actually several sections in this time history here. The first section there is about 2 hertz with a smaller amplitude of vibration. And then the next one is about 2.5 hertz with a larger amplitude of vibration. And then we have no longer moving, but just tilted really far in each direction. And then we have a super variable frequency and amplitude vibration where it's kind of just going crazy, right? It's just tilting back and forth in every which way. Then we actually in the pitch test, we had to take a little break because it started raining and you can't run a wind tunnel while it's raining. So we had to take a pause. And then we come back and we see some more chaotic vibration, this time in the midst of non-constant wind speed. So we see on the bottom, we see constant wind speed for the first section, except for that little hiccup there, which I'll discuss in a minute. And then we also have some non-constant wind speeds. That blue line, it's going up and down. We can see several peaks there. It's actually a loop played on the flow field modulator. And so we are regularly changing wind speed in a way that we're able to resolve here. And so we can see that, we're resolving the wind direction. The wind direction is relatively constant, except for the little hiccup. And the wind speed also, same deal. Now, roll tests, we sort of have a similar hiccup there in the middle where we have really large roll angles. Same test here, 2 hertz, 2.5 hertz, variable frequency. And you can see we have the same peaks there because it's the same loop played on the flow field modulator. And so it's the same simulated hurricane, and we're able to resolve all those wind speeds and directions. Now, both of these had little hiccups, right? We had a little hiccup there with the large pitch angles, and we had a little hiccup here with large roll angles. And so, but generally speaking, we're able to resolve. For most of the situations, we're able to resolve our wind speed and direction. Now in pitch, we have underreporting when it's pitched into the wind and overreporting when it's pitched away from the wind, right? If we look back here, we see when it's pitched forward, we have a little bit lower wind speed. When it's pitched away, we have a little bit higher wind speed. We can actually attribute that to the boundary layer progression. Everybody just now that from wind tunnel has been talking about boundary layers, and we see that the velocity of the wind increases as we move up through the boundary layer. And so actually when we're doing the pitch test, if we look back at this image here in the setup, when that sentinel pitches back, the anemometers actually move up because they're set a little bit forward from the rotation point. And so when I pitch it back, it moves up. And so now we're actually in a region where the wind speed is a little bit higher. And so that's when we have it pitched up, that's when we have a little bit faster wind speeds. When we pitch it forward, we're moving them a little bit down. And so we actually see a little bit slower wind speeds. And so that little hiccup there can actually be attributed to that. But in the roll test, we see kind of a symmetrical effect, right? It's a little bit overreported in both cases. But in the roll test, it's, if we look back at this image of it, this is of the roll test, right? You can see it's tilted sideways. The anemometer is pointed to the side, and so we're rolling the sentinel in the wind tunnel. In both cases, the anemometers are going to move a little bit down, if anything, because they're no longer set forward from the axis of rotation of the roll test. But that doesn't really make sense, does it? When they move down, but we're seeing increased wind speeds, that's the opposite of what we saw in the pitch test. And also, it's significantly larger. If we look at the size of the little hiccup here, it's pretty small. If we look at the size of the hiccup here, it's significantly larger. And so this is a little bit interesting. We see some kind of unexpected behavior with large roll angles. And so that's something that we need to investigate further because it's something to do with the instrument response to these skew wind angles. So we see that in the roll test, the anemometers are set up almost 90 degrees from the actual wind speed. And so when we see those really large angles, we're resolving some inaccuracies in the way that they're reporting our wind speeds. And so that's one of the things we got to do. One of the things we got to do in the future. Instrument response characteristics with the large roll angle issue, but also additionally standardization. Standardization is where we deal with this storm surge, right? This flooding. Sometimes the water gets up to 5. We can even have breaking waves up to 7 meters on the Sentinel, and so our instruments are only 5 meters off the ground at that point. The ground being relative because the ground is moving with the water. Now, normally in meteorology, we want to deal with 10-meter measurements of wind speeds. We want to have our instruments at 10 meters. And so when our instruments are at 5 meters, that doesn't tell us what we want it to tell us. But if we know that it's at 5 meters, we can actually do an extrapolation and say, okay, well, this is what we expect the wind speed to be at 10 meters. And that's just as useful. And so that's something that we're working on in the future. If you actually look at this bottom plot here, this is the plot of each anemometer's individual angle against the wind speed, against the actual wind direction in the roll test. And so we can observe that we have that red line kind of stays up at the top. It's around 1.5, right? But it's actually pi over 2, close to pi over 2. So that's what I mean when I say we're about 90 degrees off from the wind direction. When we're in the roll test, we have really big angles between the wind angle and the anemometer angle. And so we can see some unexpected behavior. So some learning outcomes. We're set up for the 2022 hurricane season. Hopefully we'll be able to deploy the Sentinel because we haven't deployed it in a hurricane yet. And so that'd be really exciting to get actual real life data with the Sentinel, putting it on the coast and having it flood and having it still work as the steel lattice towers would not work. That access to the coast should really be able to inform our discussion about wind load standards. Everybody's been talking about, our building codes. Our building codes are based on our measurements of actually extratropical winds, not even hurricane winds. And even our limited data on hurricane winds with the steel lattice towers is really contaminated by the fact that we can only put them in residential areas off the coast, several miles from the coast, that we saw in that earlier image of Southwest Louisiana. And also this data could have impacts on the storm surge modeling. If we look at how high this storm surge is rising in these different positions on the coast, depending on where we're putting the Sentinel, that could be really informative. Also, if we're able to put this LiDAR that we've been working on up on the top of the Sentinel, we'll be able to observe how much the beach is eroding over the course of a hurricane. So that could be some really informative stuff. Now, my experience at UF, biggest highlight for me, a picture on the right, I learned to surf. Never been surfing before, and it's like my favorite thing. I enjoy surfing so much. In the middle there, we see actually 2 alligators. They were eyeing me. They really thought I would be a tasty meal and they could take me down together. One on the right was actually pretty decent size. I'm not sure scale here, but he was like my size. He was pretty solid. Also this summer I broke my foot. That was really great. It's still a little bit not quite healed, but that was an experience. And also here, I think this is the picture of a sunset with a sunset and like a thunderstorm in the background. It just like looks cool. So definitely some cool sunsets, cool thunderstorms in Florida. So special thanks to everybody at the wind tunnel in particular. Vic and Ian are particularly helpful. They great technicians at the lab. Thank you so much to them. Scott Powell, lab director, great guy. We love Scott. Thanks Kurt Gurley, Brian Phillips, UT, everybody at the Powell family lab, and Robin Nelson, thank you so much for everything you do for us. Thank you. Yeah.
Is there a site you guys have in mind for where to deploy for?
Well, that depends on the specific hurricane landfall. So there's a bunch of towers. We currently are deploying 2 steel lattice towers and hopefully 2 sentinels. Currently, we can only deploy 1. That's the one that's actually possible to deploy. But also other universities, Texas Tech, Clemson, they all have their own weather stations that they also take out. And so SMP generally coordinates various locations to put them in good spots. I could have shown you an image of like that Hurricane Harvey wind record where all the towers were in particular, because some of them experience the eyewall passage, some of them don't. It's really a situation by situation basis for sure. The image of the Sentinel setup that I showed you, that was actually, I believe, in South Carolina, just to set it up to test. So I'd use South Carolina.
Is the team that is building and designing and like using the data from the Sentinel the same as the wind tunnel team, or were they just there using the facility?
Huge overlap. All the towers are stored at the wind tunnel. The data is used for scaling in the wind tunnel. All the same researchers work on deploying the towers as work on tests in the wind tunnel. So huge overlap there, if that answered your question. All right, no more. Thank you.
Hello, my name is Daniel Koval. I am a student at the University of South Carolina, and over the summer I participated in the REU program hosted by NHERI REU. Today I'll be presenting on deep learning based friction modeling of dry interfaces for structural dampers. So first I wanted to talk about why do we model friction, and it turns out that friction is a very hard thing to model sometimes. It has a lot of nonlinear properties which are hard to model, such as rate dependent behavior, which is dependence on velocity. There's also hysteretic behavior, which is also the Strybeck effect, which is that static friction is larger than greater than kinetic friction, and that can create what's called the stick slip phenomenon, which is what's being shown here in this bottom video. So this is a mass with friction being pulled by a spring, and it starts in the static domain, but once the force is great enough, it'll be pulled into the kinetic domain, and then it slips all the way back forward. Also specific to the system that we're looking at today is the what's called the backlash effect, which I'll be discussing further later on, but it's the loss of friction during reversal of travel. So this is the system that we are modeling today. It's called the Van de Greuter friction device. It's a friction-based structural damper designed to be installed in buildings and then dissipate energy which enters into the building through vibrations, either from an earthquake or from wind loading. The way it works is that it has an internal drum which rotates against the stationary friction band. Over here we can see the how the band is laid out. It's double wrapped around the drum. The first wrap is singly wrapped, then it splits into 2 and it's wrapped once more. And what's unique about the BRFD is that it is able to be semi-actively controlled. And what that means is that to some extent we can control the amount of friction which is produced by the BRFD by modifying the tension force which is going into these bands. And that's done with 2 electric actuators which are connected to either end of the band. So here's a picture of the entire BRFD test setup. To the left, we have the BRFD, and then to the right, we have a hydraulic actuator, which feeds in the desired displacement profile. This could be either from a predefined displacement profile, or it could be from a hybrid simulation. Data is collected in 3 spots. We have a load cell connected to the hydraulic actuator, which measures the friction force output by the BRFD. There are also 2 load cells connected on either side of the electric actuators, which measure the tension force on the bands. So here we have a test of the BRFD, and this is actually from a hybrid simulation. What I wanted to show is looking at these actuators, you can see that at any one time, one is being pulled into tension while the other is more slack. And that's related to the direction that the BRFD is moving. So as it's moving to the right, the left is pulled into tension. As it moves to the left, the right is pulled into tension. And so that's important to understand the effect that I'm going to show next. So an important characteristic of the BRFD is that it can produce a really large amplification of friction force compared to the relatively small applied force which comes from the bands. And how it does this is with something called the self-energizing effect. Effectively, as the drum rotates, it'll grab a hold onto the bands and pull them forward, and that increases the pressure that's applied from the bands onto the drum, and it also increases the friction force. So the self-energizing effect is a good thing. That's why it can produce such a large friction force. However, there is a side effect called the backlash effect. Once the drum changes directions, there will be a time where the self-energizing effect depletes in one direction before it can be reinitialized in the other direction. And that results in a drop of force. Here you can see a force velocity hysteresis loop. And as you enter into the backlash region, you see force levels off before the self-energizing effect kicks into place in the other direction. So for running tests, we ran two sets of tests, a set of characterization tests and then a set of validation tests. The characterization tests were from a predefined sinusoidal displacement profile, such as what's shown over here with a ramp up period, a few full cycles, and then a ramp down period. And in these characterization tests, the frequency of the sinusoid and also the initial applied tension of the bands were changed. And in total, we produced 24 data sets. And then after running the characterization data sets, we collected validation data by running 5 hybrid simulations where we simulated the BRFD as being installed in a structure while it was undergoing wind loading. So at this point, I've described friction modeling, the problems associated with it, and I've also described the BRFD. Now I'm going to describe the approach that we took, which is termed physics-informed machine learning. And so for a physics-informed model, we would have a part that's physics-based and then a part that's machine learning-based. For a physics-based, we chose a model called the Lagrange model, which is a rate and state model used to describe dry friction, rate being dependence on velocity, state being that it has an internal state variable, which means it can capture hysteretic effects. Over here, we have the equations for the Lagrange model. And then down here, there's a diagram representation of the Lagrange model, which basically represents friction as contact and deflection between two surfaces, which make contact with bristles. And the Lagrange model is commonly used because all of its parameters have physical interpretations. So there's two sets of parameters. The static parameters, kinetic friction, static friction, and the Stradbeck velocity. And then the dynamic parameters, which are just called sigma naught, sigma 1, sigma 2. Today we'll be focusing mostly on sigma naught, which has the physical interpretation of being bristle stiffness. So we're going to use the Lagrange model for our physics part. However, on its own, it can't capture the normal force, which is what's necessary for semi-active control. And it also can't capture the backlash effect. So what we're going to do is augment the Lagrange model by providing real-time parameter updating. So as the model is running, we're going to be continuously updating these 3 parameters: static friction, kinetic friction, and sigma naught. Static and kinetic friction are related to the changing normal force, and then sigma naught is related to the backlash effect. So the neural network model that we chose to do this real-time parameter updating is the long short-term memory cell. Down here, there's a diagram of all of the calculations which go into an LSTM. It's not necessary to go over everything, but what's important is that they receive time series input, which for us is going to be band tension, and produce a time series output, which for us will be those parameter predictions. And along the way, it propagates an internal cell state, which means that it can remember from and make inferences based on the past. So on to model training, we want these LSTMs to produce estimations. We're using machine learning to train it. Since machine learning is effectively an error minimization process, we need to be able to produce an error, which means we need to have true values. And so for static and kinetic friction, that's easy to do because we can look at the data and grab static and kinetic friction very easily. Static friction is just friction when velocity is 0. Here's the same force velocity graph. And then kinetic friction is the friction everywhere else. So the first step of training is to train an LSTM model just to predict static and kinetic friction. However, when we look at sigma naught, this approach doesn't work. First off, because sigma naught is not an easy value to grab from the data in the same way that FC and FS is. We also expect it to change along the course of a single test. So in this region, we would expect a higher sigma naught value. And then when entering the backlash region, there would be a much lower sigma naught value corresponding to the lower rising rate of friction. So instead, we used an indirect approach to train the sigma naught predicting model, where we actually found error from the final prediction that was outputted by the Lugre model. And then using machine learning backpropagation, we propagated that error back into an error associated with sigma naught and then trained the LSTM model on that. So now on to results. To provide a comparison, we trained one Lugre model to each of the parameterization or the characterization data sets. So we had 24 data sets. We produced then 24 separate Lugre models. Over here, we have error reported in a normalized root mean squared error. And as we expected, these models cannot capture the backlash effect. So here we have the force velocity plot. The Lugre model is in blue, the experimental data is in orange. And just like you say, this is roughly the same slope along this entire region. And it's not showing those 3 separate regions before, during, and after the backlash effect. So then we can go on to looking at the results from our physics informed model, and we see a decrease in error from 4.5% in those Lugre models down to 2.8%. And that mostly comes from the ability to capture the backlash effect. So now looking at the model versus experimental results, we see that it is able to capture these 3 distinct regions and provide a better fit to the data. In addition, now we have the benefit that we accomplished our goal of having one machine, one model. So that means that this could also be used in semi-active control. However, when we apply this model to the validation data, it doesn't look as good. So instead of having an error of 2.8%, the error is now up to 14.7%. So it's a very huge increase. And we can hypothesize why that is. Over here, I have 2 plots that indicate potential reasons. So one is that we looked at the force distribution that came from the characterization data set and from the validation data set, and we see that the validation data set is heavily skewed in the negative direction compared to the characterization data set, which is mostly symmetric. And actually, we know the reason for this. It comes from the fact that our hybrid simulation was from a wind event, and that means that there was an initial displacement that was given onto the BRFE, and then it was vibrated around that initial displacement. And so that's what produced this asymmetric result. In addition, we performed a frequency analysis on the displacement profile from the validation data sets. And we saw that although the majority of the frequencies are less than 1 Hertz, there are also some components at around 1.4 Hertz and 2 Hertz that are greater than 1 Hertz. And since we only ran characterization tests up to 1 Hertz, those could represent effects that were in the validation data set that we did not train for in the characterization data set. So this kind of leads into what future research or future improvements to this model could be. We'd want to expand the frequency sweep of the characterization data set and also the tension range that we provided. And we could also perform tests where there was an initial displacement and then vibrations around the initial displacement to simulate what wind loading looks like. Okay, so now I want to talk about my experience at Lehigh. I wanted to thank first my mentors and also everyone else that was in the NHERI project with me. They made this summer really fun. I got to meet and hang out with all of you in the office and also outside. And it was great. We also met a lot of people who weren't working at NHERI, but they were also working at either Atlas or up at Lehigh on different projects. So we always got to compare our projects, and that made the summer a lot more fun. So for our takeaways of this summer, I said subject expertise in natural hazard engineering. We also were able to advance our professional identities, both in the by networking and then also in the career development seminars. And then I also put next steps because this RU prepared us for applying to graduate school and also facing the challenges that are going to come with graduate schools. And I put my overall takeaway as accurate models for friction dampers can help us improve structural design, increasing safety and lowering costs. As far as what's next, my mentors and I want to use the work that we developed here as the basis of a conference paper. And we've actually already submitted an abstract to IMAC for next year. And also, of course, the goal is always just to survive the semester. So I wanted to thank the NSF awards that made this research possible. I also wanted to thank Lehigh University, the Lehigh Experimental Facility, and the Atlas Research Center for hosting this work. And in particular, I would like to thank Robin Nelson and Chad Cusco, who organized the NHERI portions and the Lehigh portions of this project. And without them, this research would not have been possible.
So when you're looking at your errors and you have like a 2%, you went to 14%. Were you given a tolerance of where you couldn't go above a threshold where you had to redo the whole research?
No, because right now this is it's an exploratory phase. If there's two potential applications for developing a model like this, we could either use it in creating simulations, or we could also use it for controlling the semi-active component of the BRFD. So as we get further to applying these models to one of those two cases, we would be able to set desired tolerances on the model.
Hi, good morning. My name is Edith Cardona. I am from the University of Puerto Rico at Maya West. During this summer, I worked with the characterization test of pressurized sand damper using the Boquan model at Lehigh University. The purpose of this research was to develop a numerical model that will mimic the behavior of the actual physical damper, pressurized sand damper that we had at the lab, which is an energy dissipation device that could be implemented into structures to dissipate the force that will go into it during an earthquake. In order to do this, we use the Boquan model to mimic the behavior and create our numerical model. And at the end, we were able to put to the test the damper through the model into a 3-story building code. The pressurized sand damper that we used for this research was created and was provided by the South Methodist University. And here we can see the actual damper that we had at the lab and some of the important parts that it has. Starting from the left to the right, we have the rod that is the one that will go inside of the cylinder that will move back and forth, creating the friction between it and the sand. Here we have the cylinder that is filled with sand, and the water load cells, which are the ones that will help us keep track of the inner force that is going into the damper. Then we can see here the characterization setup of the whole thing, starting with the actuator, which is the one that helps us apply the force into the actual damper. And it's connected with the rod, which is the one that it's going to be pushed by the actuator inside of it. Then going on with the load cells that I already mentioned, and finally the reaction columns and the support beams, which are the ones that are the rigid bodies that will help us support the actuator and the damper. Here we can see some of the actual damper from the inside before and after filling it with sand. Here we can see the rod that goes inside of it that has a sphere in the middle, which is the one that helps us create the friction between it and the sand, creating the damping effect that we want from the damper. since we've already introduced the actual damper, we can move on to see the numerical model that we created. In order to do this, we use the Bowman model that consists of 8 parameters, but only 4 of them are dependent on the data that we collected. And the Bowman model consists of 2 elements, the friction element and the Bowman element. Here we can see the friction element that is represented with the rectangular shape of the plot, and I'm sorry. And the Bowman element is presented as the pinching edges on the end of and the amplitude. In order to find the friction, we had to multiply the strength of the damper and the strength factor, and to find the Bowman element, we have to find the yielding force and C, which is a dimensionless inner factor that consists of a simple differential equation that we were able to solve using the numerical method Runge-Kutta through a MATLAB code. Here we can see the 4 parameters that are the ones dependent on the data that we collected, starting with C, which is the pinching factor that gives us the pinching edges and the amplitude here. And then the strength factor, that is eta, that controls the thickness of the plot, and then beta and gamma, which are the hysteresis shape control parameters, that it's basically the frame of the plot. Going through characterization tests, it's possible to replicate the behavior of the damper and then verify and modify the numerical model that we created so we can match the actual behavior of the damper as accurately as possible. So then the numerical model could predict the behavior of the damper without having the physical actual damper, and we can use it as a real we can assume that it's the real behavior of the actual damper. Here we can see one of the characterization tests that we run at the Atlas Research Center. And if I press button, maybe start. If we wouldn't have sound, we could have heard the friction the sound of the friction that is being created through the rod. You can see how the actuator pushes the rod inside of the damper, that it's creating the friction. Whenever the actuator is pushing the rod, it's creating the negative displacement, and whenever it's pulling it, it's creating the positive displacement, creating the force that goes up and down. So here, with this test that we ran, we can get this plot that we have right here, which is this force displacement loop of the open model that we created. Here are one of the model fitting that we did, the 3 megapascals pressure, 0.25 hertz, 1-inch amplitude, and the 4 parameters that we will able to get. We did this with the particle swarm function, and after applying some fine tuning, we were able to accurately match the behavior of the damper. The real behavior of the physical damper is the blue line, and the model, the numerical model that we created, is the red line. We have the force displacement loop and the velocity one. Here we have another set of data, which is the 4 megapascals, 25 hertz frequency, and 1-inch amplitude, and its respective parameters. Finally, we were able to put to the test the damper through the numerical model that we created into a 3-story building code. The scale factor that we used was 1/100 to match the scale of the building that we had. And we basically, what we did here was to apply a pressurized sine damper into each floor to verify the efficacy of the damper through the model that we created. Here we can see the acceleration and displacement reduction on each floor in the Kobe earthquake in Japan. The uncontrolled line is the black one that represents each floor before applying a pressurized sine damper, and you can see the control line is the blue one, representing how it would react after applying a pressurized sine damper on each floor. And you can see the reduction in acceleration and displacement, which is what we basically want. Here we can see the reduction, but in percentage, in 3 different earthquakes: the Landers, Kobe, Irpin, and Italy, and we can see that all of them are above 40%. That is basically what we want, proving the efficacy of the damper. Finally, after putting to the test the pressurized sine damper through the Bowman model, we were able to see how efficient it is, and hopefully in the future it could be installed into real structures since it's a low cost and simple jet effective device, energy dissipation device. Maybe in the future it could be installed to mitigate real natural hazards with earthquake, hazards. For future research, this numerical model that we created, its target is to be able to predict predefined displacement and also be implemented into hybrid simulation, because we're not able to put 100 dampers into the lab. So that's why we actually create the numerical model to predict the behavior without having the actual thing. So we can run as many tests as we want, as big, as little, and different type of samples. My experience at Lehigh, it was really fun. I got to do some work in the lab, and also we had a bunch of outreach activities with little kids. So we got to introduce engineering to them, and I gave a little buildings that they made. This one is called the rocket. I remember the name, and the other one, is the pineapple. And and here are the people at my size. I wouldn't survive this summer without them, so I like to thank them for all the support that they gave me, Jamie, Daniel, and Josue. Thank you so much. And my 3 main takeaways are the time management skills that I got from this experience. Everything had a deadline, so we had to stick to that. The learning sources, I learned a lot from this experience. Mostly MATLAB stuff, because I have never touched MATLAB before, so that was a big thing for me. And also I got to see how it would be a real work experience and see myself in the future as a professional, which is a great thing. And how this could be used, well, to mitigate earthquake, the pressurized sand damper hopefully in the future could be implemented to real structures to mitigate earthquakes damage. And finally, my future plans after NHERI, well, definitely NHERI exposed me to grad school, so I saw a lot of things that I could consider in the future. And for the acknowledgements, I would like to thank the National Science Foundation for funding this project, and also the South Methodist University for providing the sample. And I would like to thank also my mentors, Dr. Lian Cao and Dr. James Sprinkles, for all of their support and the feedback that I got them through all the summer. So, some references, and thank you so much.
Well, good morning, everybody. My name is José Antonio Díaz Ortiz, and today I will be presenting you my research on the real-time NHERI simulation of a self-centering cross-laminated timber wall system with pressurized sand dampers. This is a research that develops on the previous topic that we were talking about. So it's basically the implementation of the sand damper into a real building. This research was developed alongside Dr. Lian Cao and Dr. James Rickles from the Lehigh University, and also Calfas Costas and Dr. Nikos Maklis from Southern Methodist University. The reason why we are doing this research is because we want to assess natural hazards to the structural elements of a building. We want to prevent the cyclic loads related to winds or, for example, earthquakes, and to damage the structure, causing cost and also posing risk to humans. And so what we are doing is that we are using a tool, which is the real-time hybrid simulations, to assess the effectiveness of this newly developed damping mechanism on a particular structure. We have chosen a cross-laminated timber wall material, and we're using another type of mechanism, which is the rocking wall. And I will get to all of this in just a second. But first, let me explain you a little bit about energy dissipation systems. Energy dissipation systems are designed to dissipate the kinetic energy caused by accelerations in the form of vibration or in the form of heat, and thus preventing damage to the structure that we are targeting to protect. As examples, we have tune mass dampers, we have viscous dampers, we have base isolation or floor isolation systems, which we'll be explaining a little bit later. And they have been thoroughly assessed in literature. In this particular example, we are using rocking walls. And basically a rocking wall is an example of a structural element, it is a wall, that instead of being anchored to the foundation and fixed, it is allowed to lift and rock in this motion when it is excited with accelerations. In that sense, it can dissipate the energy in the movement of the wall. And also we will be talking about the pressurized sand damper. I will just give you a very quick review on what the sand damper consists. It is a metal case which is filled with sand. As we can see over, here. And basically it's pressurized with this cap that has 4 rods on the 4 corners of the sand damper. We keep measurement of the internal pressure because we can control the amount of force that the sand damper can develop using the pressure of the sand. Also, it's got a rod that passes along its longitudinal axis, and it is connected to the foundation on one side and to the structure on the other. In that sense, when the structure moves for some sort of reason, the rod will move along the sand, generating friction, which will dissipate the energy. Now that we understand what energy dissipation systems we're considering for this, we are assessing, let's explain how we are assessing the effectiveness of the pressurized sand dampers. We have developed a structural model. It is basically the structure that we can see on the right on map 3D. We have chosen a material which is cross-laminated timber because first, because it's a new material that is sustainable, and also it's got large deformation capacity. Also, we wanted to use this material because of the rocking wall. In Atlas, there is a rocking wall mechanism, rocking wall that is on the lab, which have been previously measured, and we wanted to match the properties to some sort of benchmark that we could compare it to. And in that sense, we have developed the building plane that we have that we can see over there. It's a 200 feet by 100 feet in plane and then 20 feet height and retail building that will be located. Located is theoretical, but it will be located in Los Angeles, California. And in that sense, we have used ASCE 716 to design the base, the weight of the building and the composition of the building, trying to calculate a base shear that is basically the shear force that the structure will be feeling to fall within some constraints. And basically in each of these base of the structure, we have pressurized the rocking wall mechanism that we can see on the right. It consists of the wall that I was explaining a little bit before. And in that sense, it's got a post-tension steel bar in the middle that is anchored to the ground. When the wall tries to move, the steel bar will create some tensile force that will pull the wall to get the wall back to its original position. And also we have included the pressurized sand dampers on either side of the wall to create additional friction force that will prevent the wall from moving. There are 20 walls on the short axis of the building, facing the short axis of the building, and in that sense, they will be controlling the motion on that side. And also the other 8 walls are on the external walls of the longer axis of the building. What we have done is that we have simplified this model, taking into consideration only a bidimensional analysis of the shorter axis, which has 20 walls. And we have assumed that the distribution of loads will be uniform along each of the walls. And in that sense, we could simplify the model a lot because we only have to simulate one singular wall with the weight equivalent to 1/20th of the total building's weight. Basically, what we use is that created a HiCom 3D model of the structure. HiCom 3D is a MATLAB-based tool developed by Dr. James Rickles. And we have created materials and elements that were designed to mimic the properties of the actual model that we were considering. For example, we have the post-tension steel bar, which is a material that will only generate the tensile forces, but not compressive forces, because that's the way the bar will work. Also, we have the wall material, which got fibers in it to mimic the fibers of the wall. The wall base, which is designed as an elastic material, as well as the gap elements of the floor, which will only generate normal forces when the wall is pushing and nothing when it is tensed. And most importantly, we tried to develop elements for the pressurized sand dampers on either side of the wall. You will see that we don't have 2 pressurized sand dampers, but 1, and I will explain a little bit. First, we have to understand what is the characteristic of the forces that the pressurized sand dampers exert. This is the formula that Eddie presented a little bit earlier, and it was developed by the developers of the sand damper of Southern Methodist University. And it consists basically of with this characteristic curve of the sun number, we can see that we have a friction box in the middle, and also we have a pinching that is the Baldwin part of the equation, which is the increase of force as you get a larger stroke. And we try to generate a model that mimic the force generated by the pressurization numbers. But when we put that into an earthquake, which is not harmonic, but rather erratic and chaotic, we weren't able to mimic the force of the pressurization number in an accurate way that we could draw good conclusions, right? And so what we did is that we developed a real-time hybrid simulation, which consists of a physical pressurization number that is on the lab, and also a friction number. The friction number's capacity, we set it to 20 kip, which is similar to the big capacities of the pressurization number on the block that we see previously. And basically what we have done is that we created this real-time hybrid simulation scheme that is on the right. Basically the way it works is that the pressurization number will be moved with the numerical model's output, and then it will generate some force that will be measured back into the numerical simulations, calculating this response of the model in a real-time constraint, which is something that is difficult, but it can be achieved to generate accurate results. The experimental setup for the hybrid simulations we can see here on this slide, and basically we have the reaction columns that will put the sand damper, that constrain the sand damper from moving. We have the actuator that generates the stroke and movement, and also it's got a load cell that measures the force the sand damper generates. We have supports to prevent the sand damper from moving and from generating vertical forces. And also we have pressure load cells that we use to keep track of the pressure, the internal pressure of the sand damper. And now that we understand how the numerical simulation and real-time hybrid simulation works, this is the methodology that we have used to study the behavior of the pressurized sand damper. We subjected the system to foreground motions that were scaled down to the site and the site and the location of the building using what we call the design-based earthquake level scale factor. For this presentation, I will just be illustrating with earthquake in Northridge, and something that is very important is that we're measuring the horizontal displacement of the wall as a drift, which is the horizontal displacement normalized to the height of the wall, and we measure that in persons. Here we can see an example on the right of how the model can work, but I will show you the real data that we get in the next slide. Okay, so this is the results from the earthquake Northridge real-time hybrid simulations. I will be showing you on the right the pressurized sand damper, and this will be a video, so I'm explaining you so that you can look up further information. And on the left, we have the numerical model of the structure. What you will see is that there is a circle here. First, let me show you this. There's a circle, and you would see that the pressurized sand damper, the physical one, is the one that I have circled there. And there on the right, you see the strokes and the forces that it's generated. That's the real simulation in action. And if we had sound, we would hear the pressurized sand damper force and friction, which is really hard. And also there were some vibrations. Something that is very particular about real-time hybrid simulations, something that I find impressive is that the time step. We're calculating in real time with a frequency of 1/1024 hertz. So basically every second we are generating 1024 data and calculating all the information. Also, since the hydraulic actuator does not move instantaneously, we have a compensator to make up for the delay in the time steps. And also, we would something that we will be able to see if we had the sound is that there is a vibration, and we had a numerical damping assigned at the same time to reduce the high frequency noises that we get in the data to make sure that we get much more accurate data. And I'm gonna put up the plots a little bit bigger so that you can understand them better. What we see on the left are the wall response plots, And I am comparing basically a traditional shear wall. A shear wall is basically a wall that is fixed on the ground, and in that sense, it cannot move. If you push it very hard, it will eventually just break. It will not yield. And on red and blue, we have the rocking bolt mechanisms, but in blue, we have the one with damping, and the other one is the uncontrolled. What we can see in the displacement time history on the top is that with the addition of the pressurized number and the friction number, we are indeed decreasing the amount of displacement, which is something positive because we want to prevent the wall from moving a lot, which will eventually generate damage to the wall. But when we look at the force time history on the bottom, we see that the base shear, which is basically the shear forces that the wall is feeling, are not only decreased compared to the shear wall system, which is something good, but also when we compare it to a control system, we are also getting decrease in movement. So we're not only preventing the wall from moving, but also we are decreasing the amount of force that the wall is feeling. And something that I wanted to mention on the right, we have the force deformation curve of the pressurized number under this earthquake. This is real data. And what I wanted to mention is that since we are using a friction number on one side and the pressurized number on the other, we're not able to get the behavior of the sand number and basically the effectiveness directly, but we can retrieve some understanding from the curve, because if you take the area under that curve, that's force times the longitude, which is energy. So basically we can see the energy dissipation of the system if we take the area under that curve. And so in that sense, let's just pull up the results quantitatively because those were qualitative. What we have seen from the addition of the pressurized numbers compared to the rocking wall without damping mechanisms is that there was an average reduction of 24% in the movement of the wall, but with in both cases we were getting a lot, lots of reduction in the force that the wall feels. Even as I was mentioning you, with the addition of the damping mechanisms, we're reducing even more the shear force. What this means is that we can use potentially the pressurized number to prevent the deterioration of the system. And also something very particular about the sand number is that it can be inserted into a structure that is already constructed to retrofit it, right? It's not necessarily something that you need to construct with the structure in the design process, right? Also, other pros of the pressurized numbers is that they are low cost and relatively easy not only to manufacture, but also to install and to maintain, because it's basically putting the sand in and then pressurizing, making sure that you can manage the force inside, therefore that it will accept. And so it's very easy to understand in that sense. As for the next steps on this research, we will eventually like to create a 3D model of the cross-laminated timber self-centering wall and also of the building to generate much more accurate data on the response of the system. Also, we will get out of plane motion and energy dissipation information, because the wall earthquakes are not unidirectional, but they are bidirectional, and we will get some information on the movement out of plane. Also, we wanted to eventually use two physical pressurized numbers, and what we will be doing is that we will be connecting both of them to the numerical simulation to conduct the hybrid tests. And in that sense, we would get much more accurate data and we'll be able to retrieve the effectiveness of the sand damper directly instead of what we have done in this case. And also we could consider more damper designs, because we can change the dimensions of the sand damper, also the sand material, the coarse of it is finer, to change the force output of the pressurized sand damper on the system. But basically those are the conclusions of the research. And I just wanted to present you a little bit of my experience at Lehigh. It was a wonderful experience. We had tons of fun. We did some theory work as well as the computer and coding part. We also got to meet each other more in depth, as well as other than the professional part, and get to do some pretty fun stuff with the outreach activities in helping the kids find their passion for engineering. And my main three takeaways from this experience are the knowledge. I would say that I've gained a lot of technical knowledge as well as a software understanding. I've got to understand MATLAB, which I have not used before. Also networking and experiences with professionals in this area. colleagues, for example, and as well as our mentors. And also we have gotten, I particularly think I've gotten friendships from this experience. And I just wanted to finally thank the National Science Foundation and the NHERI REU program, also the NHERI Lehigh Experimental Facility for hosting the project. And also my home university, the University of Puerto Rico on Maya West, and Lehigh University. Those are my references over there. And I am done with my presentation. Thank you for your time. If you have any questions, please feel free to ask.
Was this the Northridge LA earthquake in like 1985?
I think that that is.
Okay, I'm just curious.
Okay.
1994.
Thank you. Are there any more questions? Thank you very much.
My name is Jamie Harris. I will be a rising senior at Wake Forest University in the fall. And this summer, I had the pleasure of conducting research at Lehigh University under the direction of Dr. Scott Harvey and Dr. James Rickles and my graduate student mentor, Esteban Villalobos Vega. And my research project this summer was creating a 3D model of a concentrically braced frame for real-time hybrid simulation. So many of us know that earthquakes can cause large impacts to structures, causing a lot of damage to the structure itself. But what many of us don't also recognize is that earthquakes can have large impacts on the non-structural building components, things like large pieces of equipment that you might find in a hospital or a computer laboratory. So the technology of floor isolation systems, which are a type of seismic retrofit strategy, are that they are placed on top of a floor and beneath the base of a large piece of equipment in order to decouple the base of the piece of equipment from the floor and dissipate energy from earthquake accelerations, therefore minimizing the damage to the piece of equipment and increasing the post-disaster resilience of a community. So the model that we created was then run in real-time hybrid simulation with the image that you can see of the floor isolation system that we have in the laboratory. And there are lots of benefits to real-time hybrid simulation. Some of those are that we are able to run a numerical model with the physical model together in real time, collecting real-time data and accounting for different rate-dependent effects, such as displacement, acceleration, and restoring forces. And so the purpose of this research was to mathematically model a 3D special concentrically steel-braced frame and run it in real-time hybrid simulation in order to assess the building floor isolation system interactions. So within the model that we created, the model for the building, we had a finite element model, which helps us to account for the building material and the building's mass. And we developed that finite element model into a numerical model using HiComp3D, which, as discussed earlier, is a 3D modeling software that was developed by Dr. James Rickles for use at the Atlas Center. So the building, you can see the plan view here, and it's a 3-story steel building. Has a rectangular plan with 4 bays on one side and 6 bays on the other. And so it has parallel symmetrical sides. And then you can see the dimensions of the building shown here. The building has a chevron brace frame system, and there are 8 braces on each story and 6 braces on each side. And the chevron braces help to act as the lateral load resisting system for the structure. Therefore, when an earthquake hits, it helps to stabilize the structure. So here are some additional full model details. We had a total of 450 nodes and 436 elements and 1,860 degrees of freedom. Those numbers help us to assess how complicated our model is when we are determining whether it can be compiled to be run in real-time hybrid simulation. So Our model, the full model wasn't able to be compiled and run with the full earthquake record, so we did a numerical simulation in addition and extracted the floor accelerations from that, which I'll talk about a little bit later. But the model of the building was modeled with material and geometric nonlinearities, and the geometric nonlinearities were modeled using co-rotational analysis. So here on this image, you can see the nodes, elements, and braces designated, as well as you can see the linear column in the middle, which is called the P delta column because it helps us to account for the P delta effects within the structure, as well as it contains the entire mass of the structure. You can also see additional nodes, which help to account for the eccentric floor mass, and that helps us account for load that might be off the center of the building that might happen when you put large pieces of heavy equipment in a building. So a lot of the research this summer focused on modeling the chevron braces that are used within the building, and here you can see some of those details. We had 7 nodes and 6 elements, and because we were using HSS sections as the material for the braces, we had to discretize the sections. So those numbers came out to 2 fibers through the thickness and 5 fibers through the depth. And here you can see the material type that we used, as well as the modulus of elasticity, yield strength, and stiffness hardening. But in this image, you can better see the elevation view of the building, as well as the nodes, and you can see that the types of elements that we use for the braces and the beams and columns. So for the braces, we used an inelastic element type, and for the beams and columns, we used an elastic element type. So all of this basically means that all of these components of the braces helped us to determine the load deflection behavior of the braces and verify the type of inelastic material that we wanted to use so that we knew how they would behave in the full model. So the brace models were subjected to both static and dynamic loading. And then the load deflection cycles, again, as I said, helped us to verify the brace behavior and then helped us to verify our choice of inelastic element. So the plot that you can see here shows the load deflection cycle and static loading of the HSS sections. And the HSS section used on the first and second floor was an 8 by 8 by half, and on the third floor it was the HSS section a 6 by 6 by 3/8. So, and this plot shows again the static loading cycles, but you can see the difference in the buckling loads and yield strength with the comparison of the smaller braces on the third story, and that will become significant when we investigate the how the full model behaves and see that there was a majority of the braces on the third story were the ones that deformed in the model. Here are some additional figures. So this figure here helps to show the static loading of the force-based elements, and that's what we decided to use as our inelastic elements for the braces. And you can see that this model was verified using OpenSea's another type of modeling software. And we modeled these inelastically with all inelastic members, 2/3 inelastic members, and 1/3 inelastic members. And then you can also see the dynamic loading cycle for the force-based elements that we chose. And this allows us, allows the response of the brace characteristics to be amplified. And so we can better assess their performance in the building. So we did a numerical model, a simulation of our numerical model, and we did that using MATLAB. So we ran the earthquake accelerations into the numerical model, and from that we took out the floor accelerations. And the earthquake acceleration or earthquake record that we used was the Imperial Valley earthquake in Mexico, and it was used as a frequently occurring earthquake. And you can see the time step that the data was collected in here. And then again, as I said before, from the simulation that we used, we extracted the floor accelerations for each story and extracted them in both the X and Z direction. So here you can see a video of the numerical simulation. And if you look really, really closely, it might be hard to see. You can see this brace on the third story buckle. And that's again where we saw the primarily saw the most brace deformation. And so if you couldn't see it clearly in the video, I have a figure here with the highlighted braces. And you can see that the highlighted braces and the ones that were deformed happened primarily on the third story. And so those are the results that you will see in here for the real-time hybrid simulation test, the floor accelerations from the third story. So a little bit about the test protocol for the real-time hybrid simulation. We have the experimental setup of the floor isolation system within the laboratory, which is connected to a shake table, as you can see here, and then it's driven by 3 hydraulic actuators. Then we also have 3 restraining braces that are equipped with load cells to collect the restoring forces that we saw within the real-time hybrid simulation. So we took the floor accelerations and ran them in real-time hybrid simulation with the experimental model of the floor isolation system that we had at the lab. And I have a video here where you can see the shake table motions, and this is of the third story floor accelerations. So you can see the amount of large oscillations that are happening with the floor isolation system, and the mass that's placed on top mimics the piece of heavy equipment. So that stays stable while the floor isolation system moves. So here, then we have the real-time hybrid simulation results. And these are of, so we ran 3 tests, 1 for each floor acceleration at each story, but the ones that you'll see here are from the third story, which exhibited the most brace buckling. And you can see the time step that we used, and we collected the data with the consideration of 3 degrees of freedom in the X, Z, and theta direction. So the results here show the force displacement or load displacement response for the third story. So you can see that there was a lot more movement in the X direction when compared to the Z direction. And that has to do with the strong and weak axis of the building. And then you can also see that as it moved, the energy was dissipated and it was returned to its original position. Then here you can see more real-time hybrid simulation results. So you can see the total floor accelerations from the third story, and then the total floor isolation system accelerations. And so you can see that there was a large reduction in the amount of acceleration from the maximums shown here and the maximums of the total floor isolation system accelerations. And in total, in the X direction, there was a reduction of about 69%, and in the Z direction, there was a reduction of about 70%, which means only about 30% of the accelerations are actually going to the piece of equipment. So our conclusions from this are that the presence of a floor isolation system lessens the acceleration transmitted to a piece of equipment, therefore mitigating the damage to the piece of equipment and increasing the resilience of communities and lessening the amount of economic destruction or economic damage and funding that they need to repair all of these things. Some of the other conclusions were that the 3D model was very useful for analyzing both the behavior of the building and of the floor isolation system, and then the real-time hybrid simulation is a very realistic way to assess building floor isolation system interactions and collect and generate realistic results. So some of our plans for future research are to simplify our building model, to be able to run it with the entire earthquake acceleration in real-time hybrid simulation. And then we are looking at exploring the use of buckling restrained braces, zipper braces, and gusset plates in order to strengthen our model so we don't see as much brace buckling. A little bit about my experience at Lehigh. I had a lot of fun. I got to meet a lot of great people, both my faculty mentors, my friends now at the site that we were at, and do a lot of outreach activities with young kids, teaching them about like how earthquakes affect buildings and watching their faces when the buildings fall over that were tested on the shake table. So it was really fun. Some of my takeaways are that research is a continuous process. There's always new information and there's always new tests and simulations that you can run to learn more. The importance of networking and making strong connections, both with your peers and both with your faculty mentors and professors, and then the power of support and sharing your knowledge at places like this to learn about what other people are doing in natural hazards engineering and just learning more information in general. So I would like to acknowledge and thank the National Science Foundation for funding this research, both through this program, through Lehigh University and the University of Oklahoma. I'd like to thank the faculty, staff, and mentors at Lehigh University and the NHERI Lehigh Experimental Facility for implementing the real-time hybrid simulation for us. And then I would like to thank my mentors at both Lehigh University and the University of Oklahoma and my home university of Wake Forest University. And that's it. Any questions?
Your experiment scares me when you show that the third floor is more subjugated to the stresses here. So the people that are living in high earthquake areas like California, working in these tall skyscrapers, should they be worried?
I don't think they should be worried. I think it was dependent on the size of the brace, in addition to the earthquake loading. So I think that what this shows is that there are more considerations when you're creating a model like this, such as the material that you're using or the size of the steel member, in this case, the HSS sections that you're using, that affect the stiffness of the building and therefore the amount of accelerations transmitted to it. Any other questions? Okay. Good job.
Alright, sorry. Hello guys, my name is Toby and I'm in Howard University and my topic today is non-invasive self-service modeling by open source packages. And we did this research at the University of Texas at Austin. So for this introduction, we're going to be talking about DAS. So DAS, which is distributed acoustic sensing. These are fiber optic cables and geophones are technologies that measure wave propagations. And how these wave propagation form is with the figure 1, which is on the right screen, the T-Rex shaker truck, and how this produce wave propagation is shaking it throughout the field, which I'm going to show you later in the methods. So anomalies have been located when collecting non-invasive wave data from the ground to the soils. So these type of anomalies are sinkholes, and we want to detect more sinkholes and different anomalies. So the purpose of this research is to examine the property of the Florida site. And we're also going to be talking about raw data, looking at the raw data and cleaning it up, which is what we did for most of our time in Austin. So these are the sinkholes found in the Florida site, figure 2 and 3. So the background of this research is basically locating anomalies, sex number of sinkholes, and we're also going to be cleaning raw data. And it's important that understanding these problems of a site will help save people, help save earthquake damage, and reduce flood damage, and more natural hazards. So the materials and instrumentations used in this research were Python older packages. And on the right shows you map of the Jupyter Notebook, Python itself, and OpsPy, which is an open source package. And dash fiber optic cables and mobile shaker truck were used in the experiment in Florida. So in this method, you can see on the left is a Florida site where the experiment was carried out. And on the right is the data sheet. So basically, the gas fiber optic cable was along the side of the field, which is the black lines on the right. And the smart solar sensors have been in installation in a 12 by 12 array, with each sensor 5 meters from each different horizontally and 10 meters vertically. So the smart solar sensors are the red dots, and the little orange X's are the short names of which the truck shook. So the shaker truck was used to shake the ground in 200 different directions, vertically, horizontally line, horizontally across, also known as XYZ directions. And that's how the smart solar sensors got us away from this vibration of the truck. So archiving the data, which is what we did most of our time in this research. So in figure 6, I'm not sure if you can see the code well, but basically this is how we get the time for each shot. So in the first line of code, it shows you like the big time and how you get the time of each shot from the field is to basically find a number on the graph in figure 7. So basically here we can see it's at where the graph starts rising, it's at 36. So you just go back to the code and change to 36 for the peak time. So after you change to 36, it's gonna like reduce the time where the shot was taken. So figure 8 shows you the variables like the file name, the source name, and the start time. So every shot name was linked with a serial number. Like for shot A1 was linked with a serial number, shot A2 linked with a serial number. So we had to like change the serial number once you're getting the time. And there were over 800 shots. And I had help with this with Danon and Sabrina. So figure 9 shows you like the shot names, mode, direction, and time. So we have to like identify the short names, and there are over 804, I think, yeah. So for the results, so basically what I did for my project were looking at mini-C files, trimming mini-C files, and just covering these files. So in this figure 10, shows you mini-C file 1, 2, and 3, which is Z, Y, and X. And these files, you can't open it like through any database. You have to open it through Python. So how I got this plot? Well, through a set of Python codes. So here's mini-C file component 1, as you can see. And before I get this plot, there's a bunch of codes, but I couldn't fit everything here at once because it's a long notebook from Jupyter. So this is very important because without these file paths, you can't open the mini-C files. So here we have the T-Rex trigger file, hammer times, and directions. So I'm going to show you a screenshot of the T-Rex trigger file just to show you like an idea of how it looks like. So variables and directory paths. So here we have like the short names, the directions, and times. So you can print out the short names, date, times from the Excel spreadsheet that I used. So you can just like print out these stuffs and put it up here. So I'm not going to read this line of codes, but basically this is how we trim the mini-C files and how we print out the timestamp for these files, the start time, and the components. And this is the plot I showed you earlier. So basically in this results are a base set of codes written in Python, and the function of these codes is to open up file directories, so that trigger files, and these have short names, times, dates, and in the third line, in the Chiming Moon component mini seed file slide was basically a set of codes that were used to train each component of a mini seed file to produce data records, and those are what mini seed files are. So this is the screenshot of the trigger T-Rex file. All the screenshot of the first 30 or the over 800. So mini files are concatenations of data records. These can be opened through a set of Python codes, and this unique data set will be publicly available, allowing researchers to perform their own experiment with the data. So when this experiment is finished, it will be free data, and we're going to give it out to researchers, and they'll be able to conduct their own experiments with this data that we're going to provide to them. So in the future research, what questions remain after research? So how the data will be distributed to researchers, what will be the final result in the experiment in the next 5 months? And my next steps in the research is just keep checking up with the experiment. So my experience at UT, in the top left is the T-Rex shaker drop, and it's 10 minutes away from here. The second picture, second picture is the first week of my stay at UT Austin, and we did a hackathon, and that's me and my friends learning Python codes. The third picture was me at the Kendrick Lamar concert that I went with the RUs. The bottom left shows me at a soccer game, and the right bowling. So my takeaways were basically learning Python coding skills. I learned Python in high school, but it was kind of blurry. Then research skills, my first time taking the research internship, and learning about engineering as a computer science major, and how your research can be used to mitigate natural hazards. This data will help researchers evaluate the current state of practice regarding sinkhole detection. And after the NHERI REU program, I'll be looking at more internships that will help me, and I'll pursue a bachelor's degree in my field. So I want to thank my mentors, Dr. Clayton, Asser, Abbas, Isabella Corey, and Julie Cocker, and Dr. Cox, obviously, for guiding me throughout the internship. I also like to thank Dr. Nelson for choosing me and for organizing all these programs. And also like to thank Daniel and Sabrina for helping me throughout this summer. So references. Also, I think NSF also. Sorry, I forgot about that.
Any questions?
Hey everyone, I'm Sabrina and I'm a rising junior at Rice University. And so for my research this summer, I looked at non-invasive site characterization using HRV measurements. And so for introduction, I used a lot of surface wave propagation data, and we used a really large unique data set, and it's being made available for public use. And so this data can essentially just be used to characterize the subsurface. And current methods for site characterization oftentimes can be cost intensive and timely and invasive, and they don't typically demonstrate variability across a site. And so that's because these invasive methods are things like drilling or cone penetration tests, which require you to like have a specific point in the site to gather your data from. And say there could be an anomaly like somewhere else in the site, but you might not pick up on that because it's just from that one point. And so this research examines the possibilities of using non-invasive subsurface imaging techniques to detect these anomalies at a high resolution. And so for background, there are typically 3 steps when it comes to surface wave testing. And that would be acquisition, processing, and inversion. And so acquisition is just you're gathering the data, and then processing, you create a dispersion curve of frequency versus phase velocity. And inversion is the 3rd step, and that's where you create a shear wave velocity profile versus depth. And so for acquiring our data, we used DAS and geophones. And so DAS is distributed acoustic sensing fiber optic cables. And so both of these technologies essentially just work to collect near surface seismic data of wave propagations. And so studies have found that these can be interchangeable for high resolution multi-mode surface wave dispersion data. And it's actually been found that DAS has a higher spatial resolution than geophones, which means that it can acquire data from up to hundreds of kilometers away. And so the image on the right essentially just shows them laying out the fiber optic cables at our site. And the image on the left shows one of the Smart Solo geophone sensors in the ground. And so what I did mainly this summer was processing using HRV measurements. And so HRV measurements essentially just estimate the fundamental resonance frequency of a site. And they can also illustrate site variability if you use a map to plot all of the frequencies. And so HRV measurements are the horizontal to vertical spectral ratio. And so these are curves that are constructed from the Fourier amplitude spectra of the horizontal and vertical components of ambient noise recordings from a 3-component seismometer. And so the image above shows a soil profile and the Fourier amplitude spectra of the vertical and horizontal components. And because this is a 3-component seismometer, there's X, Y, and Z. And so the horizontal components, X and Y, have to be combined for this to work. So there's a few different ways to do that. There's geometric mean and there's azimuthal variability. And I'll get into those both later. And so essentially, these are used to create a HRV curve. And the lowest frequency peak will be is the site's fundamental resonance frequency. And so to do these measurements, a log normal distribution is used, and there's also a frequency domain window rejection algorithm, which basically just rejects any outliers. And so the 3rd step, which is future research for now, because there wasn't time to do that this summer, is basically inversion. And there's a few different ways to do this. There's ambient noise tomography, there's full waveform inversion, and these will basically create a 1-dimensional shear wave velocity profile. But this shear wave velocity profile may not be able to demonstrate all of the complexities of a site. So current research is being done to work on creating 2-dimensional and 3-dimensional shear wave velocity models. And so the image on the bottom just shows a pseudo 3D shear wave velocity model constructed from 2-dimensional shear wave velocity cross sections. And so for our research, we used the T-Rex mobile shaker trucks, 3-component Smart Solo sensors, DAS fiber optic cables, sledgehammers, Python, Jupyter Notebook, and HBSR Pi package. And so for our methods, Toby explained this all earlier, but we basically had a 12x12 array of Smart Solo geophone sensors, which are the red dots, and we had a 1920 channel DAS cable, which is the black line. And we had the shaker truck shake in 3 directions, horizontally inline, horizontally crossline, and vertically at each of the green X's. And we also took sledgehammer impacts, which were a vertical impact at 286 spots. And We also recorded ambient noise and took a tap test to determine the different channels in the cable. So Toby talked a lot about this, so I won't go into too much detail, but we basically spent around like half the summer working on archiving all the data to bring it into a usable format. So we essentially identified the shot name and location, mode, direction, and the exact time for each shot by comparing the field notes to the recorded measurements taken by the shaker truck. And so we read all these files and we trimmed it down to the listen times of the files for both the DAS data and the smart solo sensor data. And so for my results for the H/V method, the first step was to look at if I should use geometric mean versus azimuthal variability for the code. So I used the HBSR package, which is available from Joe Van Tassel. And so the image on the left shows the geometric mean method, and the image on the right shows the azimuthal variability method. And so the time records on the left are applicable for both. It just shows the time records for each of the three components of the seismometer, so north, south, east, west, and vertically. And then the before rejection image on the left just shows the larger standard deviation range by the red bar, which is used before the window rejection algorithm was applied. And then after rejection, that bar is like a lot smaller. So in both cases, we want to use the frequency domain window rejection algorithm. And so the azimuthal variability one, you can see there's a lot more like white dots on there. And that's just because this is taking into account spatial variability, which means that throughout the site, like if you were to take the H/V curve at like say 0 degrees versus like 90 degrees, those could be very different if the site has like a high spatial variability. But if it has a low spatial variability, then those would be pretty similar. So this just took into account like the multiple degrees that the H/V curves could be looked at. So I compared the two methods at a few different points. This is just like one of the sets of data for the files I looked at. And so I calculated the range for the lower and upper end of the standard deviation for geometric mean and azimuthal variability. And so I found that for azimuthal variability for this site, sometimes it wasn't in the geometric means range, but the geometric mean was typically in the azimuthal variabilities range. But ultimately, I decided to go with using azimuthal variability because it did account for spatial variability, even though the geometric mean method is more commonly used. It wouldn't be wrong to use azimuthal variability, so that's what I went with because the site has some spatial variability. So I also had to choose the parameters within the code. So I essentially just tested 3 different files, parameters, and looking at each parameter individually. And so I chose a azimuthal interval of 15 degrees, which means that the H/V curves would be computed for every 15 degrees. And I chose a window length of 60 seconds, which means that, and for a lower frequency peak, you would want a higher window length. And I chose lower and upper frequency bounds of 0.2 and 20. And so this will just restrict peak selection. And I use 3-hour low noise files. So I use these to construct an H/V map. I basically took the absolute coordinates of the smart solo sensors and I plugged that into Google Earth to produce the image on the left. And then I calculated all the frequencies using the H/V code and then wrote a code to create a color map of all those frequencies with the local coordinates of the smart solo sensors. And I overlaid those 2 images, produced the H/V map on the right. And so this H/V map, you can see that there's significant lateral variability across the site, ranging from 3.5 to 7.5 in the frequencies. So these changes in frequencies occur because of changes in the average shear wave velocity or the depth or thickness of the site. And that relationship is shown on the left. And so a larger frequency will indicate a shallower rock or a stiffer soil column. So because these are larger frequencies, that probably indicates that we have stiffer soil. And so the next steps for this would be to process the remaining data and work on inversion of the data to create a shear wave velocity profile and build a 3D image of the subsurface. So in conclusion, HRV maps are pretty useful for gathering the fundamental site frequencies and assessing lateral variability, which could potentially indicate anomalies in the subsurface, but we would need to do further inversion to figure that out for sure. And so this data set has been made available for public use, and it's one of the largest data sets of its kind. And so there's a ton of different ways that this data can be used. And so my experience at UT was really fun. I really enjoyed Austin. I went to a bunch of different concerts. So there's like 5 Seconds of Summer, Big Time Rush, and there's Coin on here. So that was really fun. I went tubing, that was fun. And then the lower right image is us standing in front of the shaker truck. And so my top 3 takeaways from this experience are learning how to code with Python and working with stuff in geotechnical engineering, because I had never really been exposed to that before. So just learning things like methods for site characterization and how that can mitigate natural hazards like sinkholes. And I've also learned that I really enjoy Austin. I never thought I would enjoy Texas in the summer, but it's been really fun. And so my future plans are to finish my bachelor's in civil engineering and in earth science and get a master's degree. And so I would like to thank my faculty mentor, Dr. Clayton, my graduate student mentors, Aster, Jody, and Isabella. And I would also like to thank Dr. Nelson for leading this program. And thanks to Jaden and Toby for working with me this summer. And thanks to my friends and family. And also thanks to the NSF funding. Any questions? Yeah.
Did you make the maps in HBSR Pi, or how did you develop the spatial like HBSR maps?
Oh, the like the HRV map, like
Yeah.
Like the one on the right?
Yeah.
Oh, I created a code in Python. So
Okay.
yeah.
Did you use like HBSR Web too, or like find like differences between? Was there a lot more you could do with HBSR Pi versus? Did you try it?
I didn't use the web version
Okay.
at all. I just used HBSR Pi. Yeah.
I have a question from Dr. Brady Cox. He says, Sabrina, great job. Did you use 3 hours of noise data during the evening or during the daytime when there was more traffic?
I'm actually not sure which file I used. I just used, one of my graduate student mentors had cut me a 3-hour low noise file. So that was the one that I had used. Very much.
So as Sabrina mentioned, there's a lot of different ways that we can use the data we collected this summer to create various types of models. And part of what I looked into this summer was creating models utilizing Parity, which is an open source package from all the surface wave data we collected this summer. I guess to address, my name is Danny Klaus. I'm entering my final year of undergraduate studies at Montana State University this year, and I was also part of the NHERI REU Texas Mobile Shakers group, along with Sabrina and Toby. And excuse me, Zoom listeners, in case I start walking around. I like to walk when I present, so there's a chance I forget to use the mouse to help you guys out. But just as a little bit more introduction, you guys have already heard quite a bit about this project from Sabrina and Toby, so I won't harp on this too heavily. But again, we're trying to create this extremely large data set to make available to researchers around the world so that they can create models in whichever way they see fit and kind of find analyses that come along with that. And one such application that we're hoping this data can be used for is to help better locate and size sinkholes, of which there are many in Florida. And the idea is that we'll be able to locate these by finding anomalies beneath the surface. Here you can see a photo, you've already seen it a couple times now, of sinkholes that were observed at the site. And the way we want to do this is by using non-invasive subsurface imaging techniques. Sabrina kind of addressed it earlier, but these are going to potentially be a lot more robust than existing techniques. such as standard penetration and cone penetration tests. Again, these really only give you an understanding of the in situ conditions, and sometimes not even that, of a single point on an entire site. So if these non-invasive tests are as effective as we hope they can be, in the long term, designers are going to be able to have a lot more robust understanding of the conditions that exist beneath the earth. So there's been a few models that have been created in the past using these techniques. Dr. Cox and Hawal created these 2D profiles from a similar test and created the pseudo three-dimensional profile you can see here on the top right. Sabrina discussed that a bit earlier. And then also here we have a 3D rendering of the shear wave velocity profiles. And this was actually performed at the same site that we collected data from. So this was done back in 2020. So this is how we knew there were in fact existing anomalies beneath the site. The testing methods they used for this test had a much smaller array though. So we wanted to kind of increase the size of that and also use the DOS cable to potentially have a better kind of more accurate idea of what's going on at this site. So again, you guys have kind of heard it over and over now, but we're using surface waves to kind of record and figure out what's going on beneath the soil here. And this is typically done using guidelines that were published in 2018. Those are the guidelines we followed to perform a lot of this. And again, digital acoustic sensing is a pretty awesome alternative that we're discovering from the typical geophone or smart solo array sensors setups that have been deployed a lot more recently. But one of the really cool applications of the digital acoustic sensing method, if this does kind of become a little bit more mainstream, is there's a lot of existing fiber optic cable already buried under infrastructure everywhere, basically. So if we can tap into that, we won't even have to excavate to put in geophone sensors for new construction projects to create soil characterizations. We can just hook into a Google or a Facebook fiber optic that's buried anywhere and kind of get that same ambient noise reading data from whatever traffic is moving around there. So the materials and instrumentation to do this, again, our sources were the vertical impact source or a sledgehammer hitting the ground, ambient noise, which we personally didn't work with, or I personally didn't work with a ton, but there was a special focus on the surface waves that were produced from the T-Rex mobile shaker truck. So, and for my modeling specifically, I was looking at the readings done using these smart solo sensors. So again, here's an aerial photo of the site as well as a map to kind of help you understand where Newberry, Florida is. For those of you who are at University of Florida for this summer, there's a chance you maybe even visited the near area, who knows? And then again, the sinkholes that were observed on site. You've seen this a couple times now. I don't have to go too deep into it, but here you can see what shot we call shot outside north 1. So what that means is it's to the north of our 12 by 12 array, and it's the first one from the origin here going outward. So there's 3 shots in the north direction here. So what I did is I focused on the shot that was taken here using the T-Rex mobile shaker truck when it was shaking in the Y direction relative to the site. So what we got as far as output from the smart solo sensor is the mini seed files. You guys have heard about those a couple times. This is kind of the entire layout from the entire site testing period, as well as the 15-second trimmed interval that we see. So what we had to do was, in order to get this into pair view, we had to convert it way too many times. First, we took 3 mini seed files. So the X, Y, and Z component of each individual sensor had to be combined into a single MATLAB file that reads the X, Y, and Z wave amplitudes at each of those 144 locations. From there in MATLAB, I don't have a graphic of VTK because there's not really a visual piece of it, but we converted from MATLAB to a file type called VTK, in which we needed the wave amplitude at a specific point in time, and we needed the sensor location, and we also needed that specific point in time. It's 15-second clips. Our time step was 0.004 seconds, so there was almost 4,000 time intervals for each one of these. And then when we moved into pair view, we've had to start out by setting up our sensor array layout here. And so there again is our 12 by 12 array. This is a vector reading of the sensor W1 and U1. But this is from time step 1, so it's pretty much just ambient noise because of those 15-second clips. The first second and a half and last second and a half are before the truck is actually doing any shaking. So we realized, let's not waste our time trying to create like an entire screenshot of time step 1 because that's meaningless. We want to see the actual wave data. So we arbitrarily kind of selected a spot that we knew there would be wave readings. So at second number 2, that's a half second into the wave readings beginning, time step 500 in this case. This is what we got. And it was pretty cool to kind of see the vectors laid out. However, the readings are so much more significant on that W row, since that's closer to the location of our source, that you almost can't even see anything there on the southern end of the site. And then here's an animation that we made when we got time incorporated into the system. However, this video is 12 minutes long, so I'm going to show you a trimmed version that is actually a lot more useful and starts off from the get-go. So here you should be able to see the wave begin to propagate throughout the different sensors and move through the entire array. It turns into chaos pretty quickly though, so it's a little hard to discern a whole lot of information. But so this was done, so like I mentioned, there was almost I think it was 3,751 time steps in that 15-second clip. So we started from time step 250 and clipped it at like 3,000 just because you basically saw just a bunch of dots outside of those time periods. And even then, the arrows get really small here pretty soon. And this is, they're already kind of scaled down a decent bit just because the variability from row W to row A, so north end to south end, was so significant because you can really only see vectors at row A for a pretty brief period of time during that animation. So like I said, it's a lot more significant readings we're seeing in row W than row A. But the weird part about that is we would expect that to happen when our source is going there because yeah, it's a lot closer to our source. That's a very significant movement going through the ground. But the ambient noise kind of was a little curious to me as far as why we were still getting so much larger vectors on the W row as opposed to kind of the southern end on row A. And we kind of expect this because I didn't realize this until having a discussion with my grad mentors. There's actually a road on the north side of the site. So that being our source of ambient noise, we're probably going to have a lot higher readings over there. But it was kind of weird not seeing the wave propagate as symmetrically as we would have expected, because you guys all saw that. That turned into chaos like right away. It didn't take any time at all. But in conclusion, again, this is going to be available to researchers around the world to kind of create their own models and animations to visualize what's going on at this site in their own ways. This is simply one way we're looking to do it. We're still looking at ways to improve what we see there so it's not just complete chaos. But again, we have the steps that were done to perform this pair view visualization recorded. So if people want to adjust it in their own ways that they see fit, they can do as such. And one of the ways we're actually looking to adjust it in the future is we're going to normalize the vectors. So what I mean by that, those row W vectors that were so massive are going to become, or they're going to have a max size of 1 because we're going to divide them all by whatever the biggest amplitude is that you see the entire time. We're going to do the same thing with row A. So that way in the entire array, there's going to be 1 maximum size that everything is going to have. So you're going to see it propagate a lot more smoothly. So you don't just have like invisible arrows and arrows that take up like half your computer screen. Again, another way that kind of this is going to keep going on is this is only one shot. There's like almost 800 shots that the T-Rex performed at 260 different locations in 3 different directions, as well as I think Sabrina said it was around 280 hammer strike shots. So I guess my number was a little bit off.
Mine could have been off. I think I was going off of you.
No. And then once we have these different shots at different locations, we're going to be able to compare them across the board to see if there's oddities we're noticing in the wave propagation from pair view at certain sensors. So then that way we're going to be able to hopefully locate and size these anomalies. So here's a couple photos from my summer at UT. It was pretty eventful. We got to see the bats. I know everyone's been hearing about that ever since Austin got brought up, as well as trying breakfast tacos here at TAC. I got to go to an MLS game for the first time. That was really exciting. Stadium's actually just on the other side of the road here. Here's our team in one of our many Zoom meetings. There's exciting, cool turtle pond on campus. Got to hang out with some turtles this summer. And I didn't get to feed them like Bernard, but I'll take what I can get. And then we actually got to do a really cool tour this summer of the Boring Company, one of Elon Musk's companies. However, I was required to sign an NDA, so this is just a generic photo from the internet that I got from the webpage. And then, yeah, I also have a photo here of the University of Texas Stadium, where although we didn't get to visit for any football games, that's something I'd like to do in the future because there's a lot of school pride on that campus. So as far as my personal learning outcomes from this summer, I would say creating effective communication for research is almost as iterative of a process as actually performing the research itself. As well as there's very exciting technology coming down the line for the future of civil engineering. These non-invasive methods to characterize sites could mean that we have a lot better understanding of a site. So that could help with better sizing drain fields to reduce flooding issues. That could mean better locating sinkholes so that you can design according for that. The possibilities are pretty robust. And then I'm a person who runs hot as far as temperature. Austin is very hot all summer long, but I managed to survive the heat and had a really fun time this summer. Austin's a pretty awesome place. So again, I'm going into my final year at Montana State, and I will be looking into either kind of going straight into industry or graduate school. A lot of that's going to be based on the feedback I hear over the upcoming next couple of months. So I would like to thank my home university and my home for the summer, Montana State and the University of Texas, our funding sources through the National Science Foundation, all the resources at TAC that were provided to help us with this modeling, as well as Dr. Robin Nelson and Dr. Patricia Clayton for being very great guidance all summer, as well as our graduate mentors, Acer Abbas, Jody Crocker, and Isabel Corey, and my colleagues over the summer, Sabrina and Toby. I'd also like to thank from Montana State, Dr. Audrey Benz and Dr. Michael Berry for helping me discover and get into this program. And then lastly, of course, I would like to thank my parents, John and Nancy Klaus. Any questions at this time?
I have a question. So in all three of your presentations, you talked about the fact that this data is going to be available publicly. My question is, will you be posting it on Data Depot, or where will it be available? Or you may not know that.
I don't know the answer right now. I mean, it already exists on Data Depot, not necessarily for public use right now, because that's where we basically pull all of our information from is on there. But my understanding is it's going to be available on there. I don't know about other sources. Potentially that'd be a good question for the graduate mentors and PI.
Any other questions?
Why was it called the T-Rex mobile shaker? Where did that name come from?
Because there's 5 different shakers. I know, I don't remember the names of all of them. T-Rex is the one that was used for this. I mean, that's a great question. I know it's kind of the most robust of all the shakers they have because it's able to shake in all 3 different spatial directions. It also is able to produce the most significant surface waves of any of the trucks. So maybe just because it's a big monstrous truck that they're like, all right, let's give this thing a pretty sweet name. So I don't know.
They will, and T-Rex, I think T-Rex and one other truck will be visiting tomorrow. We don't get to shake for multiple reasons, which we'll talk about later, but you get to see them and learn about them and kind of maybe get some hands-on with the truck tomorrow. So that'll be exciting too.
I'll say it was really cool when we got to kind of do the demonstration with the truck because you can feel a significant difference when a wave is getting sent through your body when it's vertical versus when it's shaking the ground back and forth. It was a weird experience to go through, but really cool. Yes, Emma?
I think he's this, but did you guys do the sledgehammering yourself?
Well, no, so the data collection was actually performed in May before we arrived. So sadly, we didn't get to make the trip down to Florida for all of that. But I know they were out there in the hot sun hitting the ground with a hammer.
I'm Grant Gabriel. I am a senior at University of the Pacific. That's in Northern California. It's a little town called Stockton, California. I think our student body is like 6,100, so it's a real small private class school. The good thing about it is you can get your classes. There's not a long waiting list for everything. The actual class size average is 24. So TAC was involved in this as well, and it's NHERI and Design Safe. The title of mine is the Deriving Soil Constitutive Model Using AI on Drained Soil Conditions. So the introduction. So the purpose of this research is to use symbolic regression coupled with AI to predict how the CAM-QUADE model will behave in hazardous situations. During my research, I noticed that the three important aspects of soil behavior are strength, compression, and critical state. Now, the compression deals with the volume change that occurs in shearing. So most of you that have taken like dynamics and mechanics of materials, you would know those kind of terms. The critical state is where the soil sample can experience unlimited distortions without changes in stress nor volume. And that's always important to know when you're constructing things, what type of material, what type of soil will hold up against these types of conditions. The background. So you ask this thing, what is symbolic regression? Some of you have heard this term, some of you haven't. So suppose we're given a table of numbers with an X and a Y set, where X goes from 1 to Xn all the way to the N. And then Y will start with the F of X's all the way from X1 to Xn. Our task would be to discover the correct symbolic regression for the unknown mystery function F. So one of the authors spoke about that on one of my references. Symbolic regression searches for both parameters and the form simultaneously. It is a core challenge for both physics and artificial intelligence. And I'll show you more examples of that. Materials and instrumentation. So we started off, Dr. Kumar gave us a practice math lab formula that we converted into Python using a thing called SMOP, which is called, it really stands for Small Math Lab and Octave to Python Compile. Very useful tool. Some of us on the West Coast, I've never heard Python. We use C++, Adobe, and MATLAB. And then when we find out what Python is and we can convert a MATLAB form to Python, that's excellent. So in Python, the two main libraries we have to import were NumPy and Pandas. Some of the methods that we use. We took the CAM-QUADE model in Python, applied symbolic regression using these types of iterations. So when we first got the formula, it was very, very dry, very bland. We had to adjust the number of iterations. I think it came in like 1,000 for Mendoza. So Dr. Kumar had to set it higher so we get it more accurate. Random sampling was like 50. We moved it to 500. Our input for X was P, C, P naught, and M, P naught, and PM will be explained. M is the slope that we're looking for. The output will be Q, which will be our initial shear stress. That's always important to know. So we apply the AI to do the symbolic regression. So what we're doing, we're looking for the root, the symbolic regression equation. Okay, so this is an example of a symbolic regression. So you have all these components floating out, all these numbers, all these mathematical operations. So the AI kind of looks at a pattern, it snatches it out, and it'll say, okay, we have a left stem and a right stem, and we have a major operation in the middle. So it takes the 2.2, it takes the minus sign, it takes the X, it divides it by the 11, and then it adds it to the other stem of the tree. So we're taking 7 divided by the cosine of Y. And so you can see if it's bringing order to chaos. So you got numbers floating around like in the twilight zone, and symbolic regression AI pulls it out and makes a formula out of it. So for our Python code, we had to do a lot of things to get it started. I think Della and I struggled on this for like the first 4 weeks. We were like, we're never gonna get this code to work. And so each day we would ask Dr. Kumar, how do we get past this? And I think the way it's set up, he gave us 14 or so YouTube videos to watch. That took almost a week and a half to watch all of those. Once we got that, this started to make more sense. We imported NumPy as NP, we import MATLAB Pilot as PLT, we import Pandas as PD. Importing the CBS, I was like, why do we have to import CBS? Because Python doesn't read Excel files, it reads CBS files. The Google Colab was important to import our files. We couldn't even open up anything without having Google Colab on our computer. And then we applied the given parameters, and we inputted different values for PC and P naught. I think I did 40 different variations, starting with 5, ending at 200 multiples of 5. So the results, once we were in the Python code, plugging in 180 for PC and P naught, we got the following results. Yes. So this is our CBS file on the left. That was very hard to get at first. And this is the chart that measures
deviating stress versus mean stress, and that's measured in kilopascals. So look at the red line and the blue line where they intersect. They intersect around 249, which is in the center of that chart. And then the red line, which is the CLS, which is the critical state line, goes all the way and ends around 263, which is the last chart on that line. And that intersection point is very important for finding your deviating stress, and where that would be the mean, where it would meet, and where you want it to meet. So discussion, we wanted our campaign model to meet the equation Q equals 3P plus a negative coefficient I got on mine's 3P naught. So basically, when you're plugging in your PC and your P naught, I use 180 in this situation. I didn't know that that was the final equation until I ran it 40 times. And then I got with Dr. Kumar and I said, Dr. Kumar, I keep getting the same thing. I keep saying the same. He said, that's it. So I was like, yeah, that's it. I didn't know that was it. And so then I saw the pattern. I saw the 3P and the 3 would be multiplied by, but I wasn't sure if that was right. And so that was our Q, which is our initial shear stress. It'll be whatever 3.0 P is minus 3 times that 180, which came to 540. And now we have a working CAM-clay model. What can we do with it? So by being able to predict how the soil will behave in extreme conditions, we can avoid certain disasters in the future. For example, we wouldn't want to build a heavy structure on a soil that can't handle the deviating stress or strain. And also it will tell you how much the deviating stress and strain has to be to withstand certain climate areas, earthquake, California, for instance. Future research. Now that we successfully derived the CAM-clay stress path for drained soils using symbolic regression or CAM-clay model, we can next go into the field and try other soils, samples to derive unknown constitutive models. Okay, let me talk about my time at UT. So I was very brave. I wanted to drive from California to Texas. The miles was 1,713 miles to get here. That's a picture of the fence of the University of the Pacific. And that is the great state of Texas welcoming sign. I stayed at the Duran Hall. I found out who Mama Duran was and why that hall was named after her, how she was inspirational in getting minority students in, getting them classes and counseling. That's the hall there. And the civil engineer architectural bit, that's where Dr. Kumar works on the 9th floor. And most of the time I was on the 6th floor because I wanted to have quick access. So. This is my time at TAC. So I've actually been here at UT for a long time. A quarter of my time was spent at TAC. On the left there is Jamie Powell, and on the right is Charlie Day. They were instrumental in teaching us some of the initial ways of getting in using the supercomputers and basically the Python code and some other things they taught us. That's me working at the desk, and that's me pictured with Dr. Gomez. She was the first person I saw when we arrived. She got us checked in our dorms, showed us how to use our meal card and everything like that. This right here is Stampede 2. Some of you had the tour earlier, you might have seen it. That was the one that caught my eye because the size, the painting, and the graphics. I think it was a $30 million computer built in 2016. So there's some variations of it after that that are a little bit faster. These are the meals that I used to eat. So I didn't feed the ducks, I didn't feed the bats, but I did feed myself. I had breakfast over at, there's a little dining hall across the street. It's really good. In the middle, Olive Garden. And then, of course, J2 meals. They're not as bad, sometimes inconsistent, but I wouldn't discourage you guys from going there. Learning outcomes. Okay, so top 2 takeaways. I learned how to use machine learning and its importance because, so when you're an engineering major, you're thinking, okay, I need to know stress, I need to know dynamics, I need to know shear stress, I need to know this, that, and the other structural. But the machine learning is important because it takes all of those concepts, plugs it in. So just for instance, when you're doing like 3rd order derivatives and things of that nature, 3rd orders, you can't actually, it takes a whole page almost, but the machine learning can do it in fraction of a second and print it out and give you the answer. So after you've done it on the paper and you plug it into the machine, you really start to appreciate how fast the machine is. So, wow, that's the right answer. So in the research, second takeaway, you never stop learning. So even like when we got these results, Dr. Kumar was talking about LSTM, which is long short-term memory, comparing the last 40 of the bottom pages and rerunning the code again. I mean, and then of course, different soil samples in different places that you can use it. Third takeaway, having a mentor to guide you is invaluable. We were lucky enough to have Dr. Kumar on campus. I know some of you have to use like Slack and Zoom and other that. I'm sure those things work, but having him in person is unbeatable. My research can be used to derive other constitutive models in unknown figures. So we talked about that, taking it to different areas. We'd like to take it to different areas where the pressure could be different, like maybe Maha City, Denver. After participating in the NHERI program, I'm now leaning toward going to grad school. So I used to tell Dr. Nelson, I'm not going to grad school, I'm too old. I just want to get in the work field, make some money, buy a house and retire. And then she goes in, okay, how to apply to grad school, how to write your letter. And then all these meetings with grad and who to contact in the facility. See, getting funding, it's easier to get financial aid for grad school than it is for regular school. I'm like, you know what? I think I might go to grad school. Acknowledgement. So this research was funded by National Science Foundation, NSF, the NHERI and NCO Purdue University. There are their numbers there, and University of Texas at Austin. I want to acknowledge Dr. Kumar, the faculty mentor, who's been instrumental in walking us through these processes. The YouTube videos, I'll always have those. Dr. Gomez, the one that greeted us in the picture as you saw that got us checked in our dorm. Dr. Robert Nelson, assisting and encouraging all the time, even when you think you're not making progress or not doing the right thing, or you know the program's not as good as everyone else. She's so encouraging, she keeps you going. Charlie Day, Jamie Powell, those are the people that you saw in the picture that helps with the codes. Design Safe, NHERI, University of Pacific, where I'm from, NSF, and University of Texas, Austin, where we are. These are my references. Glossary of terms, one. So you got see M in the beginning equation, that's the slope of the critical state line. Q is the initial shear stress. PC, I keep mentioning PC and P naught, those are the pre-consolidation pressures and initial mean barometric stress. So periodic stress is the difference between stress tensor and hydraulic pressure. So the stresses control the degree of the body distortion. The Can-Play model, it's a theoretical model that we didn't actually get a physical model. But to describe it would be elastic plastic hardening that's based on critical state theory, with an assumption that there's a logarithmic relationship between mean stress and void ratio. And everyone knows constitutive. What's that constitutive? Constitutive equation is a mathematical model used to describe relationship between stress and deformation. And that's it. Anyone have any questions? No. All right.
Oh, I have a question.
Go ahead.
So now that you're thinking about grad school, what discipline would you want?
So I'm a civil engineering minor, but I've also picked up engineering management as my major. So I just looked at the way civil engineers come out in the field, what they make and what they have to go through, and then what engineering managements do and what they make and what they have to go through. And one of the highest paying states for engineering management is California, where I go to school. So that's one of the things. So if I did go to get the master's degree, it would probably be in civil engineering. Thank you.
All right. Hi, friends. Okay. Hi, my name is Bella. I am a student at the Iowa State University, and I was an intern over here at the University of Texas, and we work at Design Safe. I work together with Greg. He's done a great presentation, so I don't know if I can match him, but I'll try. He said a lot, he said so many things. So the title of our research was Deriving Soil Constitutive Models of Undrained Soil Using Artificial Intelligence. So that's what we did. But I'd like to point out one thing. The research we did was very theoretical. We did not use any real material. So when you're talking about CAM clay is a theoretical material, and CAM clay stands for Cambridge clay. So it was discovered at the University of Cambridge in England, so hence the name CAM clay. So why this research? Somebody would ask, why do you want to do this? So I'd like to show you this thing. The ready-made is clay, and the other one too is clay. But both of these materials are the same material, clay. Definitely, the red one will behave differently from the one I presume is white. That's how I see it, but I think it's off-white. And this is an area before a hurricane, and that is the area after the hurricane. So there is this review on the UN website the 2004 tsunami in the ocean, in the Indian Ocean, the 2010 earthquake in Haiti, and the 2011 tsunami in Japan. Those three natural hazards combined killed almost 500,000 people. So definitely there is the need for us to do something. And that is what is bringing about this research. We wanted to help. We wanted that through this research, we have a better understanding of how soils behave during different natural hazards. So that's what we sought to do, to model the behavior of soils during different natural hazards. And to do that, we used two approaches. One was to use artificial intelligence to derive a soil constitutive model. And as Greg explained, a constitutive model is basically a formula that explains how a physical system behaves. And in this case, our physical system was the soil. So we wanted to model the behavior, but not only model it, use a mathematical formula to explain the behavior. So whenever you want to know how that soil will behave, you have that formula to go to, and it tells you how the material will behave. And the second one was to predict the stresses and the strain of a soil condition using machine learning. And over here, we use long short-term memory. I will explain later on what long short-term memory is. So what is the importance of our research? Basically, what we are trying to do is to be able to model the behavior of the soil. And this will lead to a better understanding of that behavior, and hopefully engineers and designers will have a better understanding. And when they are designing structures for natural hazards, they will come up with better structures, and hopefully that will save the lives of people, because just 3 natural hazards and 500,000 people died. So you can see that there is an urgency to do something. So that was the idea behind our research, and that is the significance of our research. So basically, this is what I just talked about. So what materials did we use? The materials we use, first of all, we heavily relied on Python. We used Google Colab. Google Colab was what we used most of the time. And we also did use Julia. Julia is also a programming language, but the fact is that you cannot do symbolic regression without Julia. So we had to import Julia into Google Colab and use it. And we also use our theoretical material, which is CAM-CLE, as I specified earlier. And CAM-CLE was discovered by Professor Schofield of University of Cambridge, hence the name CAM-CLE. Then we use PYSR. So the PYSR is a package that allows you to do symbolic regression. Then we use long short-term memory. Sorry. I think I'm pressing the wrong button. Okay, so what we did was to use a theoretical material. So how did we use the theoretical material? That is the yield surface of CAM-CLE and modified CAM-CLE. So what we had to do is to basically take this graph, code it into Python. So we basically use this graph, we put the whole graph into Python. Then that helps you to generate data out of the Python. So this is basically the data that we have. So the idea of symbolic regression is to look, so we give this data to the AI, and the AI is able to figure out, so this data, what formula fits it. And the AI will give you the formula that perfectly fits this data. So the way to validate the data, we have our data, and as I showed you earlier, this was the graph. So if you realize the graph has something called drain, and the other one is undrained. So I work on the undrained, Greg will work on the drain. So the drain is basically when you have a soil that does not have a lot of water content in it, that soil is drained. But when the soil has a lot of water content in it, then it becomes drained. So we compare our graph we basically generated this graph in Python. We compare it to the other one, they look similar, so we carry on. So the idea of symbolic regression is basically when we are talking about symbolic regression, I'm pretty sure you are all familiar with linear regression. So linear regression is basically you have points and you just put in a line. That's what we call the line of best fit to see how it matches. So the idea of symbolic regression, instead of using a line, we are rather using symbols. So you realize with this equation, Q is squared. So what symbol goes there? It is a square. Then you go to M, M also is squared. Then both of them are multiplied. So that is the idea of symbolic regression. So the way we put it inside the Python code, you realize that we have a number of iterations. Then we have the binary operations. Basically, we are telling the AI that we want you only to use a plus and a multiplication, no other mathematical operation. Then we have the unary operation over there. Then the model selection, we want you to give us the best model. So basically, the best model is the best formula, the simplest one, the fittest one. So the idea of symbolic regression uses genetic programming. And what is genetic programming? So genetic programming tries to mimic nature. So we have the theory of evolution, basically the survival of the fittest. So what this AI does, symbolic regression type does, it goes through the possible solution. So when you go through your first iteration, you have your initial solution. Then it checks the fitness of the solution to see if your solution is fit enough. If it's not fit enough, then the AI takes those set of solutions, mutates them, then crosses them over to generate a new population. So that pattern becomes a loop. So you go from initial iteration to fitness to mutation to crossover. Then it goes into a loop until the AI realizes that now I have a formula that is fit enough, I can give you. So it gives you the formula. So that's what Greg showed you. And this is what I also have. So this is a sample of my Python code. You see that it's telling you the third row over there, you see equations. So the AI goes through every equation and tries to eliminate those that are not fit enough and try to retain those that are fit enough. So at the end of the day, it gives you the best formula. So that best formula becomes your symbolic regression equation that you are looking for. So that was the part of the symbolic regression. Now, we also wanted to predict our data because it is very important that when we are doing simulation and natural hazards, you should be able to predict what will happen in the future. So we use something called long short-term memory, and I will explain why it's called like that. So the idea with this is that you have your data. So basically, the table I showed you earlier is the data that we use. The first step is you prepare your data using supervised learning, then you normalize the data. So I have this table over here, and if you look at this table very well, so long short-term memory is what we call a recurrent neural network. So a recurrent neural network is basically whatever output you have becomes your next input. So it is a recurring loop. You have an output, you put in data, it gives you an output, then that output in the next step becomes your input. So if you look at this table I have, you realize that the first three columns, they are the input. Then the next three columns come back. So this is my first step over here. If you look at the table very well, you see that the last three columns are the beginning of the second row. So in the last three columns, in the first row, I have the 2 over there. I'm just simplifying 2. Then the number that ends in 95. Then the next one, if you come to the second row, you see that those 3 first row, the last 3 columns becomes the beginning of my second row. So that is the idea of long short-term memory. So basically what it means is that like the problem with neural networks right now is that we only use the present data to be able to predict. But what this does is that it's able to remember the previous steps. So basically what you did yesterday, you can use that with what you did today and be able to predict tomorrow. But we don't want the AI to give us unnecessary input. So what the AI does, it only looks for the data that it thinks that it is important for it to be able to make a prediction. So the long means that it's able to remember the past events. The short means that it does not give you garbage. It only looks at the necessary information from the past to be able to predict the future. So that is why it's called long short-term memory. So it's long, but at the same time it's short. So that is the idea. So after doing our data normalization, we take this data. So this data is a conversion basically of the first table I showed you, because with artificial intelligence, you can't use the raw data, you have to normalize it. And that range has to be between 0 and 1. So that's what we did. Then we use this data for training. We use 60%. I mean, I'm having a long table. The values we have is about 20,000, and we have 5 columns of 20,000. So that's about 100,000. So it takes that, we split it into two, 60% for the test, for the training, and 40% for the testing. Then we design the neural network. So the neural network is basically the AI that does the learning and is able to do the prediction. So after we design the neural network, then we do the prediction. So this is basically what we have. You realize that in the first graph, that was the initial training. Then in the second graph, the AI is more learned. It was able to learn and make more accurate prediction. But how do you score your machine learning model? There is something we call the RMSE, which is the root mean square error. That's what usually most machine learning algorithms use to score their model. So we had a scoring of 0.015, which I was very happy about. Then I showed it to my mentor, Dr. Kumar. He said, you have to try it again. Then I tried on the test, and there was a slight difference. So for the test, I had 0.015, but for the train, I had about 0.020, which isn't too bad. So the discussions. So you realize that, as I was talking, I was saying that this is a theoretical work we did. So basically, what we wanted to do was to prove that, yes, you could use symbolic regression to come up with the behavior of soil. And basically, our AI was able to do that. But one thing we realized is that when you minimize the number of data that you are giving to the algorithm or the artificial intelligence, is not able to perform so well. And also, the LSTM was able to make very good predictions, which we were happy about. So for future research, what do we intend to do? So the reason why we used a theoretical framework was that we have this idea about, before we could go and do any research in the real world, you have to test your hypothesis and make sure that it works, because you don't want to go to the NSF, they give you a grant of 10 million, then you do something and realize that it does not work. Then it's published that our professor and student tried something, they were given 10 million just for nothing. That would be very embarrassing. So we wanted to use the concept that, yes, indeed, you can use symbolic regression and it will work. So the next step in our research will be to apply this to a real world problem by going to the field, taking sample of soils from the field and applying symbolic regression and see how it does. And one thing we would like to do is also add noise to our data. So basically, when we are talking about noise, you add unnecessary data to the data to see if the AI will be basically able to come up with the same formula. So the data I was having, there was no noise. It was just the common clay, but in future research, we can add noise to it and see how the AI will perform. So that was the conclusion of my research. This is my time at Design Safe. That is the Bay Bridge, beautiful sunset. And that was the cruise we had on the boat, which was extremely nice. And this is my REU side, the University of Texas at Austin, and that's my residence hall. And This is us at TAG, and that's where I work. And these are also some of the REU interns. We went to the Bay Bridge and we went mini golfing, which was pretty fun. So learning outcomes. Yes, for sure. I did learn so many important technical skills from this summer REU, but some of the things that really stuck with me is that one, graduate school is very difficult. And the second one is that when you are choosing your mentors, choose your mentors carefully. The reason why I'm saying that is that, as Greg said, Dr. Kuma was always available for us, be it on Sunday, be it at night, whatever time we needed him, he will come for us. He does not teach us, he does not give us the material, but he tells you, oh, have you tried this, have you tried that, then you go, you try it and you're successful. And I think that is the idea of graduate school. I don't want to go to graduate school and my mentor is not there. I've had experiences, some of the REUs, they only had to meet their mentor once and it was over Zoom. And the whole summer they had to work on their own, try to figure out things. And I think like being able to choose your mentor carefully is very, very important for grad school. My acknowledgement, Dr. Akuma, first of all, he's been of great help. I really appreciate what he's done for us. And also definitely the NSF for putting out this program. He taught me a lot and I believe you've also learned a lot out of it. Then Dr. Nelson and all the other ones are tagged, my family members, those who supported me through this research. Thank you very much. I would appreciate any questions.
Notice that you put down that you're interested in grad school. Do you have a particular university you're interested in going to grad school?
All right, and definitely University of Texas at Austin is one choice because Dr. Akuma is a great mentor. I really like him. So I do really like him. Yeah. So and also I kind of like to look at other universities. Probably. Any other question? Yes.
So how long do you think it's going to take to actually apply this symbolic regression into useful data?
It depends on Dr. Akuma, frankly. I have no idea what he wants to do next, but this is what we do. It depends on you.
All right, for time, thank you so much.
You're welcome.